two, 1 2, 1 2, 1 2, 1 2, 1 2, 1 2, 1 2, 1 2, 1 2, 1 2. Not being on the stream. Yeah. Hello. Hello, hello, hello. But I cannot hear you. Can you speak into the mic? Hello? Hello?
Eduardo.
Oh, hi. Hello.
Eduardo. We're good in here.
Nice. Grazie.
All right, I think we'll get started. Great. Okay, thank you all so much for being here. This is the opening of the ML Family Workshop 2025. My name is Sam. I was the chair this year. I just wanted to quickly say a few things. So we have 9 presentations today, and that's across 3 different sessions. It's 8 accepted submissions and 1 invited talk. The invited talk is going to be from Young Kiam in the afternoon session, so it's 14:45 there. Young Kiam will be talking about KML. I was looking over the history of presentations at the ML workshop, and I was surprised to see KML, I don't think, has had a presentation in maybe a decade. So I was really excited to have Young Kiam come in and tell us about all of the work that's been going on in KML throughout the years. So that'll be happening this afternoon. But right now we're about to get started with the morning session, and I'll hand that over in just a second. But before I get there, I wanted to say just a big thank you to all of our program committee. When I was assembling the program committee, we were really interested in trying to find at least quite a few people that had never been involved with the ML workshop before. So about half of the committee here has not previously been involved with the ML workshop, and what we're doing is we're really trying to put in some work to expand the community and grow it. Also, quite a few of the folks here are more local, shall we say. We're taking advantage of this opportunity of being in Singapore to invite participation from folks in China, from folks in Japan, from folks in Singapore as well, and nearby areas of the world. So anyway, I'm very happy that I think we're trying to do some work to try to get more people involved in the ML workshop, and I think it's going well. So can we just very briefly give a little round of applause to the program committee for all of their work? Okay, and with that, I will hand it over to Chris. Chris is the first session chair, and then we can get into our first talk.
Thanks. Is that on? Thanks, Sam. Yep, I'm excited to get started today with our first talk, which is going to be a really fun one. Dave McQueen is joining us remotely from approximately the other side of the world to tell us about successor ML.
Okay, can you hear me?
Yes, we can hear you.
Not too much echo? Hello?
You sound good to me.
Okay, here we go. So I'm Dave McQueen coming to you from the Oregon coast, and I want to talk about a proposal for successor ML, which I've called MSML, which roughly stands for McQueen's own version of successor ML, which is a historical illusion, if anybody gets that. Okay. So what is it about? Well, one moment. Let me see if I can find myself again. Right, there we are. So, as I said, it's McQueen's own version of successor ML. It's defined in the document that I wrote up a while ago, which is indicated at the bottom of this slide. And I'll put that up again at the end of the talk. And it's mainly a description of some changes relative to standard ML. And I view this as an exercise in microdesign language where I'm not touching the core characteristic features of the language. I'm not trying to introduce, for instance, a new paradigm into the language. And it's important to note that I'm not concerned with backward compatibility. I want to treat this as a quasi clean sheet design. Okay. So why am I doing this? Well, I started a project a while ago to basically rewrite most of the front end of the standard ML of New Jersey compiler. This is a personal project because I was fed up with various aspects of the fairly ancient implementation that started back in the 1980s. Also, I had a bit of nostalgia for the good old days of language design. If you got into this field in the beginning, around 1975 or even earlier, there was a lot of open ground and a lot of discussion of language design that ended up led to the design of standard ML over a period of years at Edinburgh. And there are a couple things which could be called settling old scores, fixing old mistakes. Certain mistakes in language design became evident to me and a few others. And we had a chance in 1995 to 1997 to work on a revision of the language, but there were certain constraints on how that came out. And so certain things that some of us would have done were not done. And so this was to some extent a chance to correct that. Okay. So I want to just remind ourselves of the basic character of standard ML. I put parentheses around the capital S in standard ML or SML because standard was a kind of a mistake as an adjective describing uh, the language. At the time that Robin wrote the original 1983 kind of core language proposal, he termed it standard ML, which was an attempt to unify various branches. The original LCFML, a slightly modified version that came to be part of Cambridge ML, done by Larry Paulson and Guy Cousineau, and the ideas from the Hope language that Rod Burstall and I had worked on at Edinburgh. So the computational model that should all be well known is strict lambda calculus, strict functional language. It's statically typed. The type system is basically the core of the type system is basically Church's Simple Theory of Types from 1940. It has a few major innovative features such as parametric polymorphism, automatic type inference, and algebraic data types, which came from the Hope language. And it also, of course, has a functional style module language. It has simple modules or structures. They have types which are called signatures, and then functions over those. Originally first order, later on, and in this proposal, higher order. Okay, it's useful to think of how ML is designed versus Haskell. These are the two main versions of functional programming in the world these days. Obviously, purity distinguishes them. ML is impure and Haskell purports to be pure. The evaluation order, strict versus lazy. Interpreted types, that is, types together with interfaces of operations and values, are represented using modules and functors in ML, and the this implicit, implicit propagation via type inference in Haskell. So the ML has a formal definition, which was it's a first order goal of the whole effort. And as far as I know, there's not a formal definition of Haskell. Some major changes. The bold ones I'll come back to and discuss a little bit more later on. Deletion of the open declaration. and which seemed like a good idea when we were doing the original language design, that turned out to be problematical. So we can do without it. I also wanted to delete equality polymorphism, the associated equality type variables represented with a hyphen hyphen, like hyphen hyphen A for alpha. Delete, going along with deleting open declarations, I would delete the include specifications in signatures, and also the module system should have the higher order functor feature that was introduced in SMLNJ 0.93 back in, which was released in February 1993. So we have a fair amount of experience with the higher order functors over the years, although they're not supported, they're not in the definition book, and therefore they're not implemented elsewhere. Some more major changes, mostly in the core language. One is that type variables that appear in expressions and expression level declarations should have a binding. And the infix declaration feature was something that was in the Edinburgh culture because of POP2, but it was a mistake to include it in standard ML. And it's also something that I've been thinking for a long time, which is that one shouldn't declare types within expressions, say in the left part of the declaration part of a left expression. And this is a bit controversial because some people are strongly in favor of this, but it kind of tends toward flattening the module and core languages. And in my opinion, that's a mistake. Another kind of convenience feature that's been missing, and people have wanted this forever, which is the ability to kind of do functional updates of records. And the simple general way of doing that is to have a kind of overlay operation on records. And so the abs type and while expressions go back to the early days and are sort of carryovers to some extent. And abs type has been superseded by having structures with opaque or abstract signatures, and while expressions are usually done by fold or some recursive function. So back to the open declarations. One problem is that if you use them too enthusiastically, you introduce too many names into your local namespace, and it becomes difficult to figure out where the names came from. The other problem is that open creates a serious problem for doing static dependency analysis between modules, which is, of course, an interesting analysis to do for purposes of such, for instance, the compilation manager CM does this kind of analysis. So here's the old style. We actually had modules that looked a bit like this, where we open up everything that is needed, just throw all these names into the current namespace, and then you use one of them, like name, and you don't know which of those 17 structures the name came from. And of course, name might be exported by multiple structures, and it just, you get whichever is the last one that was opened. And that's messy and bad software engineering, if you like. And the workaround for this that we've come to adopt informally is basically to, instead of opening structures, we give them short local abbreviations like S for symbol, et cetera, et cetera. And then in the body of the structure, in the scope of these declarations, we can then use t.name to indicate the name variable coming from the structure T, abbreviated to T, in this case types. Okay, deleting equality polymorphism. Languages tend to have some kind of generic equality. And in the past, Lisp, POP2, whatever, often in dynamic languages, but even in static languages, like Hope, one of the precursors of standard ML. So you start with certain primitive types that have their own primitive equality, say integer. And you can propagate equality for constructs like products and sums. You can inductively define an equality over a data type, such as lists. And the basic principle is that function types are not equal, do not support equality, and abstract types do not support equality, although you can define an equality operation for a given abstract type. And this means, of course, that you need to explicitly pass the appropriate equality for abstract types as part of your parameter set. So it's a little work in that sense, but equality types introduced what was essentially a type class into ML, and we don't want to adopt the type class mechanism in general, so let's get rid of this particular special case. So the problem of explicit type variable bindings, the principle is that any variable used should be properly and explicitly bound somewhere in code. So we can write a function f of x equals, and then we can refer to some type variable alpha somewhere in the middle of the definition of f. And then the question is, what is the scope of the implicit binding of alpha? And if f is one of a family of mutually recursive functions, that can get a bit complicated. Sometimes we might mention alpha in the typing of the function parameters, which tends to suggest that it might be local to this function, but it doesn't really do that. And in SML 97, we introduced a syntax for binding type variables in association with declarations like function declarations. But what I'm suggesting for MSML is that we have some kind of binding construct, and this syntax is throughout this discussion, syntax is all hypothetical. And so my suggestion here is that capital X will be a type variable, and this square bracket notation binds it, and then it can be referred to in its scope, which includes both the parameters types and the body of the definition of the function. Anyway, that's a kind of cleanup that's long overdue. There is an algorithm for inferring the binding site of type variables that appear randomly in an expression, but that algorithm is non-obvious. And everything should be obvious to people who are very familiar with the language. If you have features for whom even experts find things a little bit puzzling, that's bad. And I've always found this algorithm annoying and puzzling. Okay, so this convenience feature, this is one of the few additions. It's always been desirable to have a functional notation for updating a record field. And so the simple way, in my opinion, is to just allow kind of overlay, like overlaying an environment. A record is like an environment. It's a mapping between field names and their values. And in historically, several times, the with word keyword has been introduced and used as a record overlay operator. And we can't actually, this is strict in the sense that it's assumed that you're operating on record values, but it can't be defined as a function or operator because we have no way of expressing the type in general. And you might think about trying to express the type using row variables, kind of polymorphic type variables that range over parts of records, but that turns out to be kind of messy. So if we are going to come up with a new version of ML, a successor ML, there are a couple things that one ultimately takes an obligation to do. One is that there should be a formal definition of this new dialect, and there's a question about should we just edit the old definition, which is in a rather archaic formalism from the mid 1980s, or should we choose a new definition, formalized, hopefully mechanized? For instance, Bob Harper and Carl Prairie implemented a definition of standard ML in the 12th logical framework or theorem checker. The second obligation is that if you are going to have users of such a new language, you have to reconstitute the whole software infrastructure, the compiler, libraries, tools, and modify their code so that they compile in the new dialect. So that's a lot of work. Although after the SML 97 revision, it really didn't take that much effort to adapt rather to the changes that were made then. So it's routine, possibly partially mechanizable. Okay, to summarize, so MSML is a variant of standard ML, a successor ML, but it's mainly preserving its core character. In my opinion, nothing essential is thrown out. The things that are thrown out are not essential, and very little is added. And that's a little bit vague because in the course of filling in the details, there will probably be additional additions. The module system is one area of the design which deserves a little bit deeper rethink, I think, than the core. Because there's been in the intervening decades interesting research done on the module system by Harper and his students and other people at Carnegie Mellon, and by people like Claudio Russo and Andreas Rosberg. So there, as I said, there's the issue of if this is going to be formally defined, what formalisms should be used, and of course, then who will do it. And the project is associated with my planned work of reworking, rewriting the front end of the current SMLNJ compiler. And I'll go back, and the resources at this point are that there's a text file, proposal/language.txt in this GitHub repository, new front end in my GitHub project. And there's a chat locale venue called standardml.zulipchat.com. And there's a channel on the topic of successor ML within that discussion group. That's analogous to a Discord. There's actually a standard ML Discord group, but I, for various reasons, prefer Zulip chat, or Zulip. And if anybody wants to kibitz about this, they can contact me at my email address, dmcqueen@mac.com. And that's more or less it. If hopefully there's a bit of time left for questions. Are there questions?
Yes, thank you, Dave. Fun talk. Do we have questions? We do have some time. Sam.
Hey, Dave, this is Sam Westrick. So you mentioned one of
Okay.
your ideas was to not worry too much about backwards compatibility, but also the language that you've outlined here, I mean, it's very similar to standard ML in many ways. So it seems like there's an opportunity to get the best of both worlds. I mean, you're working on a new front end. Maybe the new front end can actually automatically migrate SML code to MSML code in many, many cases. And anyway, I'm just kind of curious to hear your thoughts on the feasibility of that.
Right. There are certain things that could be automated plausibly. And we thought about this with respect to SML 97 versus SML 90, the original published definition. And in that case, it turned out to be uh, not too hard to do it manually, so nobody ever got uh, motivated to try to write a software tool to translate from SML 90 to 97. And it wouldn't have been entirely trivial anyway. Um, there's also the idea of a tool that would translate, say, OCaml code to standard ML and vice versa. That was a big damaging fork in the whole history of the language. And there's a question about should deeper changes be involved? And we went through an exercise called ML 2000 in the 1990s, from about 1992 until early 2000s. And that involved a lot of people, both from the standard ML community and from the OCaml community and others. And it didn't work mainly because there wasn't sufficient consensus, and mainly on the issue of whether object-oriented features should be introduced into standard ML. Yeah, whenever you start loosening things up by considering changes to a language, there are many, many changes that could be proposed. And in the previous discussions of successor ML, there are quite a long list of proposed changes, most of them quite small. And there are things like recursive modules, which have been fairly deeply explored, but they don't seem to be um, uh, obvious enough. So I have a personal criterion, and it was that whatever feature you introduced into the language should be obvious to a uh, practitioner using the language, somebody who's uh, quite familiar with the language. And of course, obviousness is a subjective thing, but there are certain things that I regard as non-obvious, like um, GDTs, generalized data types. I've always considered those quite non-obvious. In the object-oriented world, the notion of inheritance and control flow associated with inheritance and all that is quite non-obvious. And therefore, I would like to have it in the language I designed. So that's roughly the answer. Any other questions?
Another question.
Hi, I'm Songhon. I'm a new student with Sam, and I'm wondering if some of the, I think some of the rules like not having open or not having abs type could be implemented at like a linter level to and try to apply that linter to something like a large standard ML code base like SMLNJ, and kind of test out the ergonomics of that, whether people actually appreciate these removals, whether people found them actually to be more of a hassle, and then with sort of like after canarying these removals, then maybe we can make a better informed decision about whether these features actually, having these features actually leads to more confusion rather than added utility.
That's a very interesting and plausible proposal. One could easily um, have a flag in a compiler that would issue a warning or even an error message if you used open, for instance. And that would quickly expose where people were using open. And if it's just a warning, they could ignore the warning. And for certain things, that's plausible. For other things, I'm not so sure that would work. For instance, with the explicit binding of type variables within expressions and declarations, one might modify the current inference mechanism to actually insert binding constructs into the code. So these are interesting and plausible, but again, somebody has to do them.
Okay, thanks very much, Dave. I think we, in the interest of time, need to move on to the next speaker, but this was a fun talk.
Okay.
Why don't we thank Dave again?
Thank you. Sorry I couldn't be there.
Our next speaker.
Okay.
I will use this mic. That means I can't walk around, which is okay. Sorry, I find it hard to talk and stand in the same place for more than a few minutes. Okay, so I'm going to talk about some work that I've been doing with one of my students. This is not his main research, but he very kindly has been helping out with this project. And this has really sort of been one of my, so unlike Dave, I'm happy to keep the language as it is and just focus on trying to make it run faster. And so a lot of what I've been doing over the last few years has been focused on making it run faster. And this is an example of that. So I'd like to start with just a little motivation. So we all know ML is a safe language. And when we talk about that, usually what we mean is this great slogan that well-typed programs don't go wrong. But it's safe in another way, which you could argue is maybe the same way, and that is that mechanisms like subscripting an array or a string or a vector, or adding two numbers where the result is not representable in the size of the machine word, those undefined operations get mapped into exceptions. And that means that compilers have to implement, and libraries have to implement checking code that detects whether those situations occur, and rather than doing something undefined, actually generate exceptions. And of course, this causes overhead, and many other languages have this issue as well. I mean, Java is perhaps one of the most widely used examples of that. Of course, new dynamic languages, et cetera, as well. So as a compiler writer, one wants to try to fix this, and I'm not the first person to address this. In fact, you can go back to a paper written by Mark Stein et al. In 1982, which tackled this issue, I think in the context of Fortran, but I'm not 100% sure that's the right language. And in fact, even earlier, Harrison, more from the perspective of just trying to optimize conditional tests inside programs. So this wasn't really about range bounds checking or anything. It was just really more about just the observation that there were lots of conditionals inside programs, and if we could optimize those at the compile time, we could make the programs run faster. And so he looked at range analysis in the 70s. And when Java came along, this whole topic got a real big boost. And there was a paper by Ross Bodek and co-authors, which is introduced some important ideas about how to solve this problem. And perhaps one of the more important ones was this notion of extended SSA. And I'll talk a bit more about what that means in a moment. And that particular paper was looking at essentially the the range tests, and it did this in terms of building up a constraint, what are called difference constraints, which is an idea that Von Pratt had introduced eons ago, I think, again in the 1970s, if I remember correctly. And then there's some other work that Sue and Wagner did, where they, rather than looking at it in terms of scalar variables, they look at it in terms of intervals. And they came up with a way that you could solve these interval constraints in cubic time. And lots of people have built on that basic framework of intervals, including the stuff that I'll be talking about. So we're stealing from all of these previous people. So we use the idea of extended SSA, but we do that in the CPS setting. We use an interval language that's very much like the Sue Wagner language, and then we use a solver that's based on some more recent work by Rodriguez et al. And I should mention that really, if you read these papers, at the end of the day, it's the Cousteaus who came up with the basic ideas about how to do this kind of analysis, and everyone else has just been standing on their shoulders. Okay, so CPS. So this is a sort of a fragment of the intermediate representation that the SML New Jersey compiler uses, extended with these pi things there. And the idea of these pi bindings is that they provide a mechanism to rename variables along splits in the control flow graph. So if you know SSA, right, you have phi nodes which provide a way to rename variables at points where control flow joins. And this is sort of the flip of that, where we want to have a way to rename variables at places where control flow diverges. And Bodick called this stuff extended SSA. There was also, around the same time, something called SSI was introduced. And you can actually even go back further to one of my former fellow graduate students at Cornell, who worked with Keshav Pengali, and they actually had an intermediate representation that in fact had exactly the same ideas in it. That was, I forget what it was called though. But the key thing about this renaming is it allows you to encode the flow sensitivity into the variable names, okay? And so what that means is that once you've done that encoding, you don't actually have to think about the control flow anymore. You can just think about the relationships between the variables. And so it gives what the data flow community calls a sparse analysis, and it's a really big win, because once you've got the constraints on the variables, the control flow just doesn't matter anymore. Okay, so there's a bunch of notation we'll have to go through. I may go too quickly, so please ask questions. So bound, so we start with this idea of bounds, and basically bounds are just integers, and we extend the integers with a bottom and top element with negative and positive infinity. And it's also, because we're working in the world of machine hardware, and we typically have finite precision integers as our default integer type. Most ML compilers do this. So I'm going to use L and U to represent the range of the least and maximum integer for some type. And in standard ML, we actually have multiple precisions, and so you would actually have to have multiple L's and U's for different types. But for now, let's just imagine we have, say, like 64-bit integers, and so L is minus 2 to the 63. And these bounds, of course, are ordered by the standard operation of ordering integers, and you can define the minimum operation and join operations. So min is the meet, join is the join. Sorry, join is the max. And You can also think about operations like addition and negation, and so from negation get subtraction on these things. But addition is a partial function because it's undefined what adding negative and positive infinity together are. Okay. So from bounds, you can then define intervals. And intervals can be empty, or they can consist of a lower bound and an upper bound. And by convention, we'll assume that the empty element is just has lower bound of positive infinity and upper bound of negative infinity. But in fact, it's useful to specify that if you construct a concrete, if you construct an interval where the lower bound is greater than the upper bound, that's the empty interval. We also have this notation, so I down arrow is the lower bound, I up arrow is the upper bound. So the intervals form a lattice as well, and we can order it by subset. So if you can think of intervals as just sets of integers, and you have the usual operations. We can also extend the notions of addition and negation to intervals as well. So this gives us a vocabulary that lets us write expressions involving intervals. And we need to add one more thing, which is abstract bounds. So these are basically just symbolic representations of stuff that we care about, but we don't know. So in particular, one of the things we care about a lot is the length of arrays. And so if A is an array, we're going to write, I sub, excuse me, absolute value or norm, whatever you want to call that, of A, and that's just the singleton interval, which is the length of A. But of course, we don't actually know where that lives in the space of intervals. It's just, we know it happens to have that rough shape. And then also we'll use the notation of I sub x to represent the range of a variable x. And the key thing here, going back to the extended CPS stuff, is that, variables, of course, are bound. They're not mutable because we're functional programmers. And we're going to have different names for variables and the different control flow branches, and thus the interval expression for a variable does not change based on control flow, because when we go from, we have like x, and then we say something like if x less than y, when we're in the true branch, we're going to have a different x. We're going to have x sub t, which is the true version of x, and in the false branch, we're going to have x sub f, which is the false version of x. And those are different variables, and thus they will have different interval expressions. And so that makes everything work very nicely. So then we have this form of constraints, and again, this is just taken from the Sue and Wagner formulation. So you have some sort of constraint expression, and then you can intersect it with a concrete interval, so not an interval that doesn't involve any of these abstract things, but has concrete bounds. And then we can say that that's in the subset of the interval for x. And basically that's just that represents the flow of information, right? The stuff on the left is what we've defining in terms of computation, and that's going to flow into the definition of x. And very frequently I is just going to be top, so we will omit it in those cases. Okay, so that's the basic framework of how we want to write constraints, and let's consider some program forms. So the first one is, let x be the length of A, and that introduces a constraint that basically just says that x is the length of A. If we have a trapping arithmetic operation, so trapping add here, so the T here means that if x plus y is out of range, not representable, then we're going to get some sort of trap raised, and so this instruction will not complete, right? So we take I sub y plus I sub z. That's the result of adding y and z together, and that interval might be bigger than the LU interval, right? It might extend past the LU interval in some way, and that would be a trapping situation. But if this instruction completes and x gets a value, we know it's going to be in the LU range, and so that's why we have the intersection with LU. So either this instruction fails if I, y, and I plus, if the x and if y and z are out of their addition is out of range, or else it succeeds, and if it succeeds, it's going to be in the LU interval. But hopefully we'll have better information than that. And then conditionals are the most interesting case. So we have a conditional, say like x less than y, and we rename the variables x and y in the two branches, and we only need to rename the variables that are actually tested, because nothing else, we've learned nothing else about any of the other variables. And so in the true branch, we're going to be able to say, well, the interval of x, and so this is the interval of x above the if, intersected with the range from the least integer up to the top of the interval of y, the upper bound of the interval of y minus 1, that should be less than or equal to, subset of the interval for xt. And we get a similar kind of expression for the interval for yt. And that's just basically expressing the information that you learn from that particular conditional in the true case, and then there's a similar thing in the false case. And I should say that in the original version of the paper, and in fact in the literature for this problem, typically people only care about the true branch, and so often use a much simpler version, just essentially saying Ix flows to Ixf and Iy flows to Iyf, which those are sound constraints, but they're not as precise as you can be. So I've actually revised the paper this morning, I think. So if you have followed the link previously, you may want to follow it again, but to have the more precise version of these. Okay, so the other place where you have to worry about generating constraints has to do with joins. And in CPS, joins are just lambdas, or functions. And we can use a flow analysis to approximate the set of call sites that call a particular function definition. Now, in standard ML of New Jersey, the flow analysis is what we might call a first order or syntactic flow analysis, which is basically the situation where f and g are the same name, the same variable. But you can imagine you might be using something like 0CFA and get much better information, and this framework would certainly let you use that better information if you had it. So if you know that there's a particular call site G that flows to this function, then we can write that yi, so the the variables of the function should be x's, so that's a typo. So that we can write yi flows to xi. So where xi is the parameter, and again, should be in the function binding, and yi is an argument which comes from the call site G. Now, normally what we do here is we say, well, if we know all of the call sites of a function, then we call the function a known function, and we can do something interesting there. But if there might be a call site that we don't know about, because we're not doing whole program analysis here, we're doing module level analysis, and so maybe the function gets put into a data structure, or maybe the function gets passed as an argument to some external function or something like that. So if we don't know, then it's an escaping function. And the other thing is we're only really interested in variables that have integer type. Because that's the only thing we're analyzing. So we can avoid worrying about most of the variables in the program. But if we know all the call sites, then we can just basically take the union over the, so for every y, that's a parameter that flows to the ith variable, assuming the ith variable is an integer variable, we will include the interval of y. So we'll just get a big union of all of those intervals, and those all flow to xi. And if it's a escaping function, we're going to have to add LU, but once we add LU, that's just going to wipe out all the other information we know, so we just put LU in there. Okay, so that's basically how we generate constraints, and once we've generated constraints, we have to solve them. And so the basic way you do this is that what we want to compute is what's called evaluation, and that's just basically a function rho that maps variables, and technically these are the ECPS variables. So it maps those variables to intervals, and it has to be consistent with the constraints. There's obviously a trivial solution, which you could just say everything is top. It's not a very interesting one, but okay. So one of the sort of challenges of our approach, and this is something that's not covered in most of the literature, but some of the literature, is that we have symbolic intervals, right? We have these intervals that correspond to lengths of things. So the work by Bodick and co had that idea, but the Wagner paper just worries about concrete intervals. So we do know some things, and it turns out that this allows us to solve, to answer most of the queries we need to answer. So we know that the interval for a length interval is going to be in the range from 0 to m, where m is the maximum supported array length. So that might be, 2 to the 63 minus 1, or it might be something smaller than that. But whatever that number is, we can you can always conservatively replace one of these length intervals with that concrete interval as an over approximation. So so the goal is to compute rho, and our approach is based on the algorithm that's in this paper by Rodriguez et al. From 2013, and the basic idea. So all of the, or I think pretty much all of the papers that we looked at in this sort of general area of the literature use a hypergraph to represent the constraint system. And the reason it's a hypergraph is because the edges correspond to constraints and the nodes correspond to variables, but a given constraint can have multiple inputs, and therefore you get a hypergraph. And one of the key tricks for performance tricks that people have come up with is this idea of first computing the strongly connected components of this graph. And in C programs, which is the Rodriguez paper is actually about analyzing C programs. For C programs, you have you typically the size of the largest strongly connected component is typically orders of magnitude smaller than the size of the whole graph. So they give an example where the largest, for one of the benchmarks they use, where the largest strongly connected component had like 1,000 nodes in it, the graph had 1 million nodes in it. So by solving these things in topological order, as each solution is computed, that populates the evaluation for all the variables in that part, and those are the variables that are you'll need later on for as you process things in topological order. So if you have a non-recursive component, which turns out to be lots of the components, maybe a majority of the components, solving the constraints is trivial. It's just really applying the evaluation you have to the variables on the left-hand side of the constraint, and that determines the value on the right-hand side of the constraint. For recursive components, we use an iterative process that involves widening to basically deal with the fact that otherwise you could get this sort of unbounded growth, and then narrowing to refine the bounds so that you actually get useful information out of it. And this is a fairly standard but an old idea, and the details are in the paper. The paper, my student wrote a very nice little description of exactly how all that stuff works. And so, okay. So once we have this valuation, we can actually use it, which is the goal of all this work. So given rho, if you have a trapping addition, you can weaken it to a non-trapping addition. If rho of the interval expression that describes the result of that addition is contained within the range of representable values. If you have a conditional, so x less than y, we can replace that with a true branch if rho of the upper bound, well, rho of ix upper bound is less than rho of the y's lower bound, right? So that means that the interval, the possible values of x have to be less than all the possible values of y, and therefore this is going to always be true. You can also figure out the false case in a sort of similar argument. Now, the paper talks about unsigned comparisons. So this is I had a chat with Fritz Heinlein the other day about this, and it was sort of realized that this is maybe not something that people know well. So it's a trick, but it's a great trick, which is that because of 2's complement arithmetic, you can do a comparison test between 0 and n by doing it as an unsigned comparison. Because if the variable, say I, is negative, it's going to be bigger than a positive n, right? Because n is, the high bit is going to be 1. And if we do an unsigned comparison, we treat that as just a very large positive number, right? And so therefore, because of that trick, compiler writers should implement subscript tests using unsigned comparisons rather than signed comparisons, because it means you only have to do 1 comparison instead of 2, and that happens to be the constraint you need to solve for that. And that is the constraint you need for that, and I'm almost done. Yeah. So we've implemented this analysis in the 2025.2 version of SML New Jersey. So this is the version that uses LLVM as its code generation infrastructure. I would say that they're still chasing down bugs, so I don't have a good performance analysis for you, but we have been able to run some things, and in particular the example in the paper, if we run it, which is just basically add up the elements of an array of integers. So this is kind of like represents the best possible speed up you could get, because it's the conditional tests dominate the code. We actually see a 57% speed up there on adding 250,000 element arrays. Obviously the speed up for bigger programs is going to be a lot worse. I would mention that there are other opportunities for optimization. So standard ML has trapping coercions. When you go from, like, say, a big integer to a small integer, you have to test whether the big integer will actually fit inside the small integer, and if it doesn't, that's causing an overflow exception. But again, that's something that range analysis might, in fact, be able to tell you is not going to happen, and you could get rid of that test. It's also conceivable that big num arithmetic could be optimized, where you could tell that you could actually get away with, fixed sized arithmetic, because the results are going to be small enough. And with that, I'm happy to answer any questions.
Yes, we do have time for one or two quick questions if folks have them. Looks like Martin does.
Great. So it seems your analysis is kind of sensitive to the propagation to the conditionals appearing directly in of the test appearing directly in the conditionals. So, for instance, if you bind first a variable b to whether something is less than something else, then you lose precision.
Yes, that's true. Although the optimizer, we run this after we've done a lot of sort of standard optimization. So in that case, it's very likely that the test would have kind of migrated. Well, there are two things. One is, and this is something we haven't experimented with, but conceivably we could iterate, we could run this more than once. And so it's conceivable, like just the way, say, contraction works well if you do it more than once.
You have the built-in order type in standard. So do you do something special with that, or
Order is something that we currently don't have built into the compiler. The compiler doesn't know anything about order. It's just a data type. So that limits some of the kinds of optimizations we could do, and that's something that I think, for other reasons, would be good to make the compiler aware of. It's
This might be too broad of a question, but I'm just curious if you have any examples of kind of bounds checks where this sort of analysis succeeds that more kind of naive approaches don't.
Yes. One of the things I experimented with, and again, this is, you know, a more detailed performance study, I would do this comparison, was just using essentially a kind of redundant range check optimization, because it's very frequently the case that you'll have a test and then you'll have another test that dominates, you know, where the first one dominates the second one, right? But one of the problems is, and one of the things that this analysis does very nicely is it deals with the fact that you have a mix of signed and unsigned comparisons. And that's actually a little bit harder to reason about, because the unsigned comparisons are, you know, are doing two things at once. And it's also the case that I haven't figured out a way to do that for the trapping arithmetic optimization. So,
Thank you.
Let's thank John again for fun talk. And our last speaker this session is going to be Mizuki Arata, who's going to tell us about his new compiler, Lunar ML.
Hello everyone. My name is Mizuki Arata, and today I'd like to present Lunar ML from standard ML to scripting languages. This is an experience report about building a compiler that translates standard ML into Lua or JavaScript. So what exactly is Lunar ML? It is a compiler that translates standard ML into Lua or JavaScript. It is developed at GitHub, and the development began in 2018. It implements the full standard ML 97, along with some extensions and part of the ML-based library. A key milestone is that compiler is self-hosting, meaning it's capable of compiling itself. However, I should note that the script compiled version runs very slowly, so it's not yet recommended for daily use. It also implements a powerful feature called delimited continuations, which I will discuss later. Why did I target Lua? The story starts with LaTeX, a LaTeX automation tool I wrote in Lua back in 2016. Perl and Lua are common in tech-related programming, and TechLive ships with a Lua interpreter called TechLua. But as as Kratec grew, maintaining it became harder, partly because Lua is untyped. So I thought, why not write a compiler that produces Lua code from a typed language? Back in 2018, there were not many choices. Till and TypeScript were just starting, and Hex felt too object-oriented for my needs. Why did I choose standard ML? I wanted to implement an existing language rather than creating a brand new one with its own ecosystem. I do like writing Haskell, but implementing it is another story. Standard ML was appealing. It has a solid definition and manageable feature set. Other candidates were OCaml, Haskell, and PureScript, but SML struck the best balance. Now, let's look at the compiler's architecture. The compiler used the handwritten lexer and ML-YAC parser. Type checking is inspired by bidirectional type checking, hoping for good error messages. Equality types are handled with implicit arguments, porting Martin Ellsman's work. Pattern matches are checked for exhaustiveness and redundancy. Modules are translated to be using the effing module approach. Finally, there is a CPS intermediate representation with second-class continuations. Here is the compilation pipeline. It goes from passing type checking, desugaring to a CPS form and optimizes there. After optimization, the program goes through another IR and target specific transformations. The CPS intermediate representation is inspired Andrew Kennedy's compiling with continued. However, unlike the double-barreled CPS approaches, exceptions are compiled differently. Continuations are second class. The backend decides whether to use direct style or CPS. Let's see how to compile second-class continuations. For Lua, compilation is easy because Lua has a goto statement. For JavaScript, which lacks goto statement, we use labeled breaks for non-recursive continuations. If the continuations are recursive, we use a combination of for and switch statements. Let's walk through a few code examples to see what the output looks like. For hello world, we can see that the Lua code calls the write method on the standard output. Note that the SML's print function flashes output and raises an exception on error. So there is some code for error handling. For factorial, we can see that integer overflows are checked. Tail recursions are converted to loops using goto on Lua. Also, the tuple parameter is unpacked. For mutual tail recursion, it is technically possible to optimize them into a loop, but I've avoided it to reduce possible code duplication. Now, let's see the JavaScript code generated by LunaML. For hello world, note that the string is represented by uint8 array in JavaScript. I will discuss this topic later. The flashing of the string is represented by passing the continuation to the write method. integer overflows are checked. Since JavaScript has no proper tail calls, Luna employs a technique called trampolines. Tail recursions are converted to loops, so it doesn't use trampolines in this case. Mutually recursive functions are not converted to loops. Even so, that program will not cause stack overflow thanks to trampolines. Currently, LunaML supports Lua 5.3 and 5.4 and LuaJIT and JavaScript. There are some variants, and Lua variants include one that use coroutines to provide one-shot delimited continuations. For JavaScript, the user can direct style compilation or CPS1. Some features are limited in the direct style compilation. Some of the audience may not be familiar with Lua, so I'll make a brief introduction. Lua is a scripting language that can be easily embedded into applications. It is used in tools like LuaTeX, Pandoc, Nginx, and NeoVim. It has proper tail calls and coroutines, but no multiplication integer. There are several versions of Lua, and they are incompatible in general. In particular, Lua 5.3 introduced 64-bit integers. Older versions used floating point numbers for integers, like JavaScript. LunaML supports Lua 5.3 and 5.4 and LuaJIT. Data types of SML are mapped as in this slide. Lua table is a hash table and can be used like records or arrays. Lua has several limitations. The number of local variables in a function is limited to 200. LunaML implements a workaround by storing excess variables in a table. Maybe an algorithm for register allocation should be employed. On LuaJIT, the number of up variables, which are lexical-free variables of a function, is also limited to 60. Again, LunaML implements a workaround using tables. The non-JIT implementation has a limitation with exception handling. I encountered this problem when running Hamlet. It can be worked around by with coroutines. LuaJIT on ARM has an issue with -0. Now let's talk about JavaScript. JavaScript is the language for the web. Also popular as a server-side language with runtimes like Node.js. It lacks proper tail calls in practice, and everything is asynchronous. Data types of SML are mapped as in this slide. The treatment of storing types will be discussed later. There are several important design choices we must make when targeting JavaScript. The first one is the problem of tail calls. We need tail call elimination in functional languages. The ECMAS standard specifies tail call optimization, but some important engines like V8 and SpiderMonkey chose not to implement it. Therefore, LunaML uses trampolines and converts tail recursive function to loops. The second problem is asynchronous functions. Both web and Node.js relies on callbacks or asynchronous functions, but SML-based library defines synchronous interface to file I/O. LunaML's solution is to use CPS transform to provide delimited continuations. I'll describe it later. The third problem is about strings. SML-based library that specifies that strings are sequences of 8-bit integers. Therefore, if we want to encode text in SML, we usually use UTF-8 encoding. On the other hand, the JavaScript string is a sequence of 16-bit integers. Unicode texts are represented by UTF-16 encoding. How should we reconcile them? SML compilers that target platforms like Java and .NET also suffer from this problem. As far as I know, SML.NET seems to use 16-bit string for SML string. SML tools seem to limit JavaScript string to 8-bit. Should LunaML just use JavaScript's native string as SML string? I don't think so. It is hard to write portable programs if the text encoding depend on the platform. I had seen a few programming environments where the format of strings varies depending on the platform, and it was difficult to write internationalization-aware programming in them. LunaML chooses to use 8-bit strings on the JavaScript target, represented by uint8 array. To access the JavaScript's native string type, LunaML introduced an additional string type, string 16. I once tried to provide it as wide string, but that idea was not satisfactory. The fourth problem is about integers. Traditionally, the only numeric type in JavaScript was number, which is 64-bit floating point number. It is still widely used today. Therefore, LunaML's default integer type should be represented by it. What about the width? 64-bit floating point number can express every 32-bit integer without loss. Should we use int32 as a default type? One of the use of the default integer types in SML is the representation of array index. JavaScript's array length is represented by unsigned 32-bit integer, and typed arrays can be even longer. If the default integer type were limited to 32-bit, an SML program cannot make use of large arrays. Therefore, LunaML's solution is to 54-bit integers as the default integer type. 64-bit floating point format can express every integer with absolute value less than 2 to the power of 53, and it fits into 54 type. Now, let's discuss the delimited continuations. As I said before, JavaScript relies heavily on callbacks and promises. I wanted to implement synchronous I/O specified the ML-based library on top of Node.js's inherently asynchronous I/O. Adding syntaxes for async and await was not an option since it changed function types, the so-called function coloring problem. LunaML's solution is to apply the CPS transform to allow programs to access first-class continuations. Some existing compilers, such as SMLNJ and MLTON, provide first-class continuations known as callcc. However, this model of callcc would not fit LunaML because an SML program can only capture calls made within SML. Therefore, delimited continuations seems to be the natural choice. With delimited continuations, the extent of stack frames captured is delimited by a prompt. There are several formulations of delimited continuations, such as shift, reset, and control prompt. Also, there is a typing extension called answer type modification, and OchaCamel implements it. However, I chose not to extend the type system, and I implement the interface suggested the paper, a monadic framework for delimited continuations, which is a multi-prompt system and general enough to express other formulations. The implementation on the JavaScript backend uses the CPS transform. The translation is based on the paper I've just mentioned. The meta continuation is managed by a global variable. I've made some adjustments to correctly save and restore the exception handler. On the Lua backend, I've implemented one-shot delimited continuation on top of Lua's coroutines. The runtime implicitly pushes a prompt called top level to allow capturing the rest of the program in certain contexts. With delimited continuations, JavaScript like async and await can be implemented as ordinary functions. They may be useful when interpolating with JavaScript code. Also, concurrent ML-like interface may also be possible, but I haven't investigated much. I want LunaML to be an improvement over standard ML. So I implemented several language extensions. Some extensions, like record extensions, are from Successor ML, and other small ones are original. I'll describe original ones. First one is UTF encoded escape sequences. SML97 has 4 hexadecimal digit U escape sequence, and successor ML has 8 digit one to encode a code point. According to the specification, they represent a single character. The natural interpretation would be a single code unit, which is an 8-bit integer for UTF-8 and 16-bit integer for UTF-16. They are not useful for expressing UTF-8 encoded text. LunaML implements another form of escape sequence, blessed one. Both Lua and JavaScript have this form. They represent a sequence of code units to express the Unicode character. They are encoded with UTF-8 or UTF-16 depending on the type. Second extension is hexadecimal floating point constants. C1990 and IEEE 754 specify a hexadecimal notation for floating point numbers. It is useful for expressing the exact value of a floating point number. For example, the max finite constant can be easily expressed. So LunarML implements it. The exactness is important. So the compiler rejects a notation if the value cannot be represented exactly. Third extension is about infix operators. SMLs has infix declarations for make identifies as infix. However, they are visually unappealing and long identifiers are not supported. Haskell uses the backquotes to make an identifier infix. They are visually appealing and can be used to make long identifiers as infix. Can we bring something similar to SML? Unfortunately, the backquote is a legal character for an SML identifier, so cannot be used for this purpose without breaking compatibility. One of the few choices is the dot, so LunarML implements this feature. Fixed can be specified by infix declarations. The last extension is about type description. In Haskell, one can write type description next to the definition. I like Haskell, so I wanted something similar in LunarML. However, adding new syntax would make the code incompatible with other SML compilers. That means such syntax cannot be used in portable programs, including LunarML itself. My solution is to write type description in a comment. With a compiler flag, this special comment is passed and checked by LunarML. For compatibility with other compilers, the special comment does not affect type inference. So where does this project stand today? The latest release 0.3.0 includes promise integration, the web target, more readable output, and type checking of intermediate language for robust compilation. Looking to the future, I'm considering adding more backends with PHP, WebAssembly, and native code with being potential candidates. There is also significant work to be done on performance, including more advanced techniques like effect analysis. Finally, I hope to build out the ecosystem with packages like DOM and web server. This concludes my presentation. Thanks.
Okay, we have time for a couple questions, if anybody has one.
Okay, so say I have a Lua API that exists already, and I want to write a program in LunarML to call into this API. Do I need to create some kind of binding to this existing Lua API to give the types of the functions in that module?
LunarML provides some types and functions to access the Lua API. So it is rather verbose and not very ergonomic.
Okay, so there's some stuff there, but okay, I think I see. Thank you.
I have a question. I was curious how you implemented type inference, in particular whether you used levels, as is common in some ML and Haskell compilers, or whether you used a more direct implementation of algorithm W.
Sorry, I'm not good at listening in English. So
That's okay. I was wondering about your implementation of inference, and whether you used. Do you know about levels, which is how like OCaml and Haskell implements type inference, or whether you used algorithm W directly?
I use level-based implementation.
Ah, great. One more question, it looks like.
Fantastic work. Did you do any test? The value representation you're using for data types, for instance, there you're using kind of these tags just as strings. It seems in your overview of data types. Would it be possible to do things like for lists, for instance, you can just use null or just test for null, so you can get a more compact representation, maybe speed up some things? I don't know if you consider that.
RML uses special representation for list. But the performance is not measured.
Okay, thanks.
All right, thank you so much for the fun talk. Let's thank the speaker again. It's now time for lunch, and the ML workshop resumes at 1:45.
Okay, welcome everybody. So my name is Sam. I'm the session chair for this session, and the PC chair. But anyway, so I'm very happy to introduce Wenhao Tong from University of Edinburgh. He'll tell us about freezing bidirectional typing.
Yeah, thank you for the introduction. So I'm going to talk about how to freeze bidirectional typing, and I'm going to introduce a new approach called FROST, which focuses on doing bidirectional type inference for first-class polymorphism. So what is first-class polymorphism? Like, as many of you may know, there are some different forms of polymorphism. Like, they are different in where quantifiers can appear and which types can use when we do instantiation. So the most simple one is the net polymorphism or pre-next polymorphism, where we only have top-level quantifiers, and we can only use monotype to instantiate type. For example, the classical polymorphic identity type. And we have higher rank polymorphism, where quantifiers can appear anywhere, but we can still only use monotypes to instantiate a polytype. For example, here we have a function which takes another polymorphic function as an argument. And we have first-class polymorphism, which is the same as higher rank polymorphism that quantifiers can appear anywhere. And we can also use a polytype to instantiate another polytype. So suppose we have a single function which is polymorphic, it creates a list, and we have the identity function. We can do the application single ID to have a list of polymorphic identity function. And so we focus on first-class polymorphism, and by type inference, we want to infer where to introduce quantifiers. Like if there is a function from x to x inside the program, whether or not there should be a quantifier outside of this function, and we want to infer where to instantiate the quantifiers. Like if there's a variable ID in the program, whether or not we should to instantiate this identity polymorphic function. And if we do instantiation, which polytype we should use, and also for an anonymous function, if the parameter is not annotated with its type, which polytype we want to use for the parameter. But unfortunately, for type inference for FCP is undecidable. This is a well-known result in the literature. And because there is an undecidable problem, there are lots of different approaches in the literature using different intuitions and heuristics or algorithms to approximate type inference for successful polymorphism. So why we want yet another new approach? Our initial motivation is to do better type inference for modal effect types, which is a new effect system based on multimodal type theory. And I'm giving a talk on Saturday morning in Uppsala. So the key observation here is that type inference for modal types is very similar to type inference for first-class polymorphism. So as I have shown before, for first-class polymorphism, we want to infer where to introduce and instantiate quantifiers, and when doing instantiation, which polytype we use. For function parameters, which polytype to use. For type inference or modal types, we want to infer where to introduce and instantiate or introduce and eliminate modalities. And when we are instantiate a polytype, which model type we can use, and for a function parameter, which model type we can use. Yes, so we observe that the information flow between we observe that bidirectional type information flow is very useful to answer these questions, but many existing approaches do not make use of this information as much as possible. And in particular, let's consider a function application M2N. There are two different directions of flows from M to N or from N to M. And so what we want to do, and we want to make use of both of these directions. So we propose FROST, which allows the information to flow back and forth between functions and arguments. And we introduce a freezing operator, which is used to control the direction of information flow if there is no best choice at all. It is called frost because frost forms when marble flows to colloidal surface and phases to acid crystals. Yeah, so I'll start with introducing the different directions of information flow in existing approaches. So first is to flow from the function to the argument, which is the most common approach in most bidirectional type systems. So for example here, if we want to infer a type for if we want to infer a type for m applies to n, we first infer a type for m, which is a, and then we instantiate a to a function type whose argument type is a1, and use the type a1 to type check the argument. As an example, we can use this information to know whether or not we should introduce some actual quantifiers to the argument. See that we have a poly function which takes a polymorphic function and returns int, and we apply poly to fun x to x. So first, we infer the type of the function, which is poly, which has this type, and then we use the argument type of poly to type check the argument from x to x. And because we know from x to x should have type for all a dot a to a, we know that there is an implicit introduction of this quantifier. As another example, flowing from function to arguments also tell us which polytype to use for function parameters. So supposing we have another function poly2, which takes a function that takes a polymorphic function, and we apply poly2 to fun x to 42. So first we infer the type of poly2, which is this type, and we use the argument type of poly2 to type check fun x to 42, which tells us that for the argument, its parameter x should have the polytype for all a dot a to a. And moreover, this information flow also tells us if we want to do some instantiation, which polytype we can use. Supposing we have a poly3, which takes a list of polymorphic identity function and returns int. And we have nil, which is the empty list, polymorphic empty list. So we first infer the type of poly3, which gives us this type, and use the argument type of poly3 to type check nil. Because nil has a polytype, we know that we should instantiate it. Yes, we should instantiate nil, and we should instantiate the variable b with for all a dot a to a in order to give the argument the type list of for all a dot a to a. So these are three examples of flowing from functions to arguments. And there's another direction of flowing from the argument to the function. So this is typing rule in the paper that arguments go first. In this paper, in addition to a normal context gamma, we also have another context, which is a list of the argument types. So when we want to type check, we want to infer the type of m applies to n. We first infer the argument type a, and append this type a to the new context for m, so that when we are inferring the type of the function, we can make use of the fact that its argument should have type a. And here is one example which tells us how to instantiate a function. So suppose we have a head function which takes the head element of a list, and we have a list of polymorphic identity function. So first, we infer the type of the argument, which is list of for a dot a to a, and this information is propagated to the function head, which tells us that we should instantiate head with for a dot a to a in order to make the argument type of head match the real type of IDS. And as another example, this direction of information flow also tells us which type to use for function parameter. So we have IDS again, and we first infer the type of the argument, which is the type of IDS. And this information is propagated to the function, which tells us that so the function is just an anonymous function from x to x. And we know that its argument should have type list over a dot a to a, which is exactly the type of the argument x. So we have seen so we have seen that in previous works we can have one direction of information flow. The question is, what if we want both of them? And here is one example where having both directions is important, where we apply a function foo. It is a polymorphic function. It takes another function from B to list of B and returns int. And we have IDS. We want to apply foo to another function that returns IDS. So if we first flow from the argument to the function, for which we want to pass the type of IDS to the function foo. And then, since we know that the function foo should take another function whose result type is the type of IDS, we should instantiate the type variable b with for all a dot a to a. And after this instantiation, the information then flows from the function to the argument. And we use the argument type of the instantiate foo to type check the argument, which tells us that the argument x of the argument from x to IDS should have type for a dot a to a. So for this example, we rather want both directions of information flow, but previous to typing rules cannot type check the example, because what we are doing here is we only propagate the type of IDS to foo instead of the whole type of the argument. So our idea is that we use skeletons, which are types with some ghosts, which represent unknown information, to represent a partial type information, and having a typing rule starting from n, starting from the argument n, going to the function m, and then going back to the argument n. So here is the same example as we have seen before. So with first, we first infer a skeleton for the argument. For this argument, its skeleton is this. So we have, so a ghost represents unknown information because at this stage, we do not know which type should be the parameter of from x to IDS. So it is a ghost. And we also have two ghosts followed by a dot, which are universal ghosts, which represent some unknown list of quantifiers, because there could be some generalization or type abstraction later, which we don't know now. So we put some universal ghosts to represent that information. And we have the property that the skeleton of a term matches any of its possible type. This is very important to avoid rejecting any valid type for a term. And then, instead of passing the type of the argument to the function, we pass this skeleton to the function. And based on this partial information, we still know that we should instantiate the type variable b of foo with for all a dot a to a, because this skeleton tells us that the result type should be list of for all a dot a to a, which should match list of b. And then we can use the argument type of foo goes back to the argument, which tells us that the argument x should have type for all a dot a to a. Yeah, and so this is the core idea of how we support both directions, and here is more details on skeletons. So, like here we define type AB like standardly with variable A, unit type, a function type A to B, or a polymorphic type, and we define skeletons almost the same as types, but with ghosts and universal ghosts, which represent unknown type information and unknown quantifier information, respectively. And we also have a set of skeleton inference rules, which I'm not going to show here, but they are very similar to the typing rules. And they allow the skeleton information to propagate through the program structures. For example, if we have a pair of functions from x to x, its skeleton is a polymorphic pair of two polymorphic functions. But that is all. That is all the information we know. We don't know anything more, like what should be the type of the x, or what should be the type of the result of the function. And also, if this pair appears inside some not expression, then its skeleton is still the same, because the skeleton of the result of this net expression just propagates through the program structures. Yeah, and another question is, what should be the skeleton of a variable? So for example, if you have a variable x of type A in the context, we really want a skeleton that is compatible with arbitrary instantiation and generalization of this type A. So for example, for ID, we want a skeleton like we want a skeleton that matches with arbitrary polymorphic function, and for pair, we want a skeleton that matches with arbitrary polymorphic function. Oh, sorry, this is a typo. But here is a typo. But we want a skeleton that should match with arbitrary polymorphic function from ghost to a pair of ghosts. So we have this meta operation hunt, which just does instantiation and generalization, but not with concrete types, with ghosts instead of concrete types. So if there is some type quantifiers, we instantiate with a ghost, and if there is another universal ghost, we just animate it, and when we reach a guided type, we introduce a universal ghost. So which is consistent to the definition of hunt, because now there are ghosts appearing in the result. Yes. And another question is, the skeleton may not be as informative as we want. And there is a very simple example to see why. So if you have a single which creates a list and the identity function, so by default, what we have enforced is that we'll infer a skeleton for the argument ID, which is ghost dot ghost to ghost. And then we'll use this pattern to get the instantiation of a single. But however, this skeleton is very useless. It doesn't tell what kind of a polytype the argument should be. Well, in order to make the type inference deterministic, we have to guess a monotype here instead of some arbitrary polytype. So we can only instantiate single with some monotype tau to tau. And then we use tau to tau to type check ID. So by default, first gives us a list of tau to tau for some monotype tau for this program. But however, if all the information goes from the argument to the function, we actually can have the type list of for a dot a to a, which is a more informative type. To see why, we have the argument has type for a dot a to a, which is passed to the function to get its instantiation, which tells us that the argument variable a should match the polytypes for all a dot a to a. So we can do a polymorphic instantiation for single. Oh, sorry. Yes, so in order to allow first to also give the type list of for a dot a to a, we introduce a freezing operator inspired by freeze ML. So for this program, we can write a user annotation to freeze ID. And by freezing it, the skeleton of ID is not ghost.ghost to ghost, but it's type for all a dot a to a. And yeah, so freezing term means its type can never be influenced by its context. And we can use its for type to get the type inference of the outside. So this type is passed to single, which tells us that we should do a polymorphic instantiation for single. Yeah, and then the polytype for all a dot a to a also, of course, goes back to ID. Yeah, and here is one more example, which is combining a more complicated argument with freezing. So first, we do a skeleton inference for the argument, whose skeleton is a polymorphic pair, whose first component is some arbitrary polytype, and the second component is for a dot a to a because ID is frozen. And then this skeleton is passed to choose, which tells us that we should instantiate choose with for a dot a to a because the second argument of the pair has this type. And then afterwards, the argument type of the instantiated choose goes back to the argument, which tells us that the first component of the argument from x to x should have type for a dot a to a. So there is an implicit introduction of the quantifier a. Yeah, and here is a table of some examples from previous papers comparing first, which is the first column, with some other existing approaches. And I'm not going to dive into the details of this table, but as we can see, first performs okay in most of these examples. Yeah, and so what I have seen so far is what we have at the point of submitting the extended abstract. And after that, I realized that there's some excellent work on Canada local type inference 20 years ago, which seems to provide a way to give a much better declarative representation of first. So since we are only caring about inferring polytypes, we have two different colors for quantifiers. One is in blue, which means they are inherited from the outside, and the other is in red, which means they are synthesized from inside. So for the previous typing rule or function application that I have shown you, it is first infers type of skeleton of the argument, goes to the function, and then goes back to the argument, which is intuitive, but it is kind of algorithmic because it more or less describes how the algorithm should do for a function application. But with colors, we can give a much nicer rule like this, where a tilde means to reverse the color of a. And the idea here is that for the type A of the argument, all red quantifiers are those we synthesized from N, so they can be used to get the instantiation of M. And all those blue quantifiers in A are from outside. They are information that are provided by M to N. So we can use colors to represent this. We can use colors to represent the information flow of these two directions simultaneously. Yeah, and yeah, so this is still work in progress. We have a declarative specification based on ghosts and skeletons, as I have shown, and we have a more declarative specification using colors. We are working on proving a simple sound accompanied type inference algorithm for it, and this algorithm is already implemented in some toy language, with support for both first-class polymorphism and for model effect types. Yeah, and I think my takeaway is we should allow type information to flow bidirectionally, and we do so via ghosts. And if there's no best choice between these two directions, we can phrase it via phrasing. Yeah, thank you.
Okay, we have time for a few questions. We have a mic right here if people would like to come up for questions.
Hi, thanks for the talk. You had that big table of examples.
Yes.
How many of those examples had to be modified with freeze annotations?
This is a very good point. So the left part of this table are taken from existing papers, and I think this is probably the only one that require freezing, which is not supported by the other approaches we are comparing with. Yes, and the right part is some examples that we made, with a few of them requires freezing. So I guess the intuitive answer is that in most of the cases, freezing is not needed, but when we want some more fine-grained control on the direction, to make some programs that are very hard to type check, then we can use freezing to do so.
Sure, thanks.
Any more questions for Wenhao?
I just had a quick one. The last example. Yeah. I was curious if it still worked if I froze the left-hand side and left the ID unfrozen. No, choose with a function. Choose with an this one. Yeah, if I'd frozen the other side, does that work? It wasn't a little unclear to me what exactly you freeze at. Whether you freeze whether you generalize and then freeze, or whether you're just going to freeze the ungeneralized type, or whether you're even syntactically allowed to freeze a constructive form.
So if choose is frozen, then it is ejected.
No. The fun x to arrow x. Can I put an ice cube around that and then not around ID? Because you know.
So intuitively, freezing term means its type must be what we can infer from inside of this term without relying on any information from outside. So freezing from x to x will give us an arbitrary model type tau to tau.
Okay, not for all alpha. It's not the most general type that you're freezing.
Yeah, so there's no generalization before freezing.
I see. Cool. Thanks.
Okay, let's thank the speaker, and we can get the next one up.
And go full screen.
Good.
Okay.
So our next speaker is Viviana Bono from University of Torino. and she will be telling us about a typed approach to ontology manipulation. So take it away. Thank you.
First of all, I want to apologize because this is not going to be an easy talk to me because I don't have any voice. Sorry about that. But I hope to convey enough information. And second thing, this is not a technical talk, neither a formal one, just more like a vision, and I hope that you don't get too bored about it. So, let me tell you a story. An ontology is a formal explicit specification of a shared conceptualization used to represent knowledge about a domain by defining possibly uniformly its concepts and the attributes and the relationships among concepts. The idea is to have a common vocabulary to talk about a certain domain and enabling machine understanding and reasoning, but not only, also human one, and facilitate knowledge sharing and data integration. So that's very important. Talking about ontologies. I'm just recalling some concepts that I'm sure every one of you knows about RDF triples, for example, that are made of a subject, a predicate, and an object, and each component can be an international resource identifier describing a resource, indicating a resource that describes a certain concept. So we build graphs by connecting those components, and this is a very Italian example. Margherita is a pizza, it's a type of pizza, and it is eaten by vegetarians mainly. Oh, sorry. Sorry. Then I'm sure you heard about OWL that builds up RDF, but is a richer language where basically knowledge is separated into two parts, two boxes. One is the T box that defines the vocabulary of the domain, in particular concepts and their relationships. Very important relation is the subconcept relation, similar to a subclass relation. And then you have A boxes, where you have assertions about individuals, for example, the fact that Margherita is a pizza, or that Gianni and Margherita are connected by a eat link. The OWL language allows you to infer properties starting from the two boxes, A box and T box, and I mean, this is a very simple inference. It's like OWL works on a subset of first-order logic, and I'm sure you can see the example by yourself. You can infer that Margherita is a vegetarian pizza because it is eaten by a vegetarian guy called Gianni. Another ingredient is XML. XML comes in various forms, and we have here two examples, RDF XML and OWL XML. RDF XML is simpler, and this is the one we used actually. And you can actually express triples as I showed before. Instead, the OWL XML is more richer, sorry about. For example, here you can see that in the RDF, pizza is actually a tag, whereas in OWL XML, it's actually an IRE an attribute of a class, so it's richer, is a richer explanation, at least in the syntax. We choose the simplest one, RDF XML, because it's the one that should be supported by any tool working on ontologies. I said already that the OWL XML is richer in syntax, but from the point of view of the expressiveness, by reification, you can basically express the same things, because you can make a verb like a subject and create a triple with a verb as the subject, as a noun, so to speak. Oops. Why am I talking about all this? Nowadays, inference is done preeminently by machine learning tools, where you actually feed the assertions to which is, you know, the propositions about the individuals to machine learning tools, and you get results, and you don't do inference in a logical way. Well, not that much anymore. So we were talking about colleagues that actually worked on knowledge representation, and they felt like there was a loss of expressivity by doing that. And so we started, it's my undergrad students, now master students, and myself, started to wonder if functional languages could actually support and enhance the standard classical well-known knowledge representation inference. And in this sense, we explored the use of SEDUCE. We have in the audience one of the fathers of SEDUCE, actually. It was born from a collaboration between groups in France. And what I like about SEDUCE is that it's actually a general purpose language, very fun to program with. And this goes beyond the fact that it's XML oriented. I will tell you about that soon. It's XML oriented because it gives a very rich pattern matching in order to check and build XML. So we thought maybe we can use it to work with ontologies with some success. First of all, on my right, there is a fragment of XML code describing a parent book, meaning people with children, and these people with children have a name and possibly a phone number labeled with home or work, not necessarily like that. And on the other side, there is the version of XML written in SEDUCE, and here you have basically the components. You have a tag, and here you see you have a gender, and then in squared brackets you have a list of elements that characterize your tag. What is parent book? Parent book is a type, and what does the type do? When we upload the XML file, basically this is checked against the type, and if everything goes well, then SEDUCE produces its own version of XML, the one on my left. So just have a look. You have angular parentheses to contain tags and attributes, and then square brackets to contain sorry, to contain elements. For example, here in this parent book, you have a person of F gender called Clara with no children and a phone number without any label about the fact that it's a home or work. And instead here you have Bob, and that has at least that has one one child, sorry, F called Alice with no children, and a phone which has an attribute home which was optional, but this is what it is now. So again, this is summarize the syntax, which is not only of the language but also of the types. You have tags, attributes, and content, where tag and content are types or type patterns. As I said, pattern matching is very beautiful in this language. So now we go to the type the XML was checked against. And here you have let's go through a couple of things. One good thing about the seduce types is that they are readable, humanly readable, and easy to understand. But basically, a parent book is a book made of a zero or more persons, and then you have F persons and M person. F person is a person with a tag person with an attribute gender assigned with F, and the rest, and similarly for M person. Then we saw the children have names, have a name and some other data. PC data represents a string, which in turn is simply a sequence of characters. And this is important in Seduce because it means that we can stick together generated strings by the program with XML already there. You have all kind of regular expressions. For example, here you have an alternative between home and work to describe the phone, and this is to say, well, it is to say that I don't remember what's that. It's optional. Thank you. Yes, because now I was getting confused with the other use where you have the non-greediness. But it's okay. Thank you. It says that, in fact, I said before that it was optional. And the rest should be quite clear because you have a normal way of forming, for example, emails with the character between sets of chars. As I said, we have types, concatenation, union, one or more times, zero or more times, and then the optionality, 0 or 1 time that I wasn't remembering at the moment. So sequences are really the core of the type system of Seduce. Let's see now other two ingredients. Functions are lately bound overloaded functions that are typed with the form of intersection types, which is another very interesting thing. And this is the form. Basically, it says that if we have an argument of type T1, we get S1 as a type for the output, and so on and so forth. And each of those clauses are a pattern that gives us an expression of a certain type when the type corresponds to the type I was saying, as I was mentioning about. I didn't say it very well, but anyway, overloaded function, so the type determines the branch that it is going to be executed. And we have map and transform that works with sequences, and map is the usual map that transforms each element recognized by a pattern. And then we have transform that instead is a filter and transform. Basically, map gives you back as many elements as the starting sequence. Instead, transform can give you back a shorter sequence. So let's see a couple of examples. Here you have a transform because you want to have a concatenate. Oh yeah, another difference is that transforms returns a sequence. Here you want to have a list of names taken from the parent book. And so you basically bind, and we will go back to this underscore, which is the wildcard as usual. But you bind the person from the parent book, and for each of the person, you basically, by pattern matching, extract the name, and you concatenate it to the names of the recursive call. What is very nice here is the use of this union type, because basically it says, well, we have to extract also the names of the children, but children is another tag, it's not a parent book. So what do? We simply do this. We put a wildcard here to say that this transformation is okay both for parent book to take the first level of the names and for children that are another tag. Okay. Then we have this intersection type use. This is a simpler example. Basically, very normal example. According to the type of the arguments, you can have either a sum if the arguments are int, and otherwise a concatenation of strings that is represented by at. Here you go by pattern matching, meaning that x and y are the argument, the actual parameters, the formal parameter of the function that will be bounded to the arguments according to the one. So this function has types couple of pair of int, arrow int, and couple of strings, pair of strings, arrow string. And now another example, which is a bit more complicated. I go back to the type I showed you before. Now the idea is to actually specify better information about people. In particular, we want to have men and women as tags, not as attributes, gender F or of M. And we want to have name not into the elements, but as an attribute. And so we basically manipulate the data structure we had before in order to get this. So what do? We write a function that is called split, and split as an intersection type because it takes either a name person and it transforms it in a man, or an F person and transforms it in a woman. And another very interesting thing here is, okay, let's read this first. Here, by pattern matching, we extract the gender of a person, the name and the children to apply recursively the transformation. Was it me?
No, I think the other room.
Okay, thank you. Then I was saying it's interesting because you can see here that tags are actually first class values because we generate an XML element, and actually we give the tag inside the program, because if the gender is matched with the F, this new tag called either man or woman will appear here in this new element we are generating. So a good thing about Seduce is not that only allows you to check XML, but allows you also to generate it in a well-formed way. So basically here what happens? It happens that for each tag M or F, we create a new element in XML with the name as an attribute, and then we recursively call here the function map. It's important that this is an intersection type because it allows you to specify the type of S and D that are going to be partitioned in sons and daughters, where sons S is of type sons and the other one is of type daughters. If we add a function person, it's not visible, person, arrow, man or woman, we wouldn't been able to type the recursive call because for each S and D sequence of male or sequence of female, we wouldn't been able to have a specific man or woman type, so we weren't able to find the right type for daughters and sons. What did we do? We basically wrote a type to describe an ontology in RDF XML. Of course, we have namespaces. We need namespaces in order to define each tag in a unique way, in a way that, I mean, the W3 does. So the string before the colon is actually the namespace, but just to go through quickly, we have an ontology has a certain tag and with certain attributes and values. It is a set of 0 or more things. Things can be ont, which is the reference about the name of the ontology, properties, class attributes that are the elements of class attributes, a notion of equivalent class, we basically left it very, very open. Subclass, everyone knows what it is, and so on and so forth. The most important thing is that in order to be able to talk about properties of individual, we left that blank because we had to, otherwise we had to hard code all the relations. For example, this underscore could be parent of, okay? Had we used the OWL XML, we would have had names for attributes for those things too. What we did was to take a thesaurus, which is basically a terminological database organized in a hierarchy, and transform it in an ontology. Which thesaurus we used? We used the Europeana Fashion, which is a multilingual thesaurus for fashion and fashion-related concepts that turns out to have also historical information about garments. What we did was porting from this thesaurus to an ontologist and then do merging of ontologies. Sorry. Maybe, yeah, I should go a bit faster. The thesaurus is simpler. The thesaurus basically has concepts which are under the type desk, and the attributes are labels, scope notes to specify better certain characteristic of the concept, exact match that sends you to the resource where basically the element is defined by the resource string, usually an HTTP site link. Then then broader is the superclass, and type is actually the name of the superclass inside this is a typo, shouldn't be green. It should be black, but I wasn't very good with my LaTeX, so it became green. Sorry about that. Instead, an ontology is a subset of what I've showed you before, and we decided to take as much as possible from the thesaurus, and we have, maybe it's better to show you some transformations. At first, we had simple functions in seduce to transform notes from scope note, which is a label of the thesaurus, to note, which is a label of an ontology. Exact match to dictionary. Broader, I said it's subclass and so on. But then we decided to write a function altogether that does all those things. So basically what it does, it matches a thesaurus. This is the sequence of thesaurus that are bounded by concept. And for each concept, we create a new class. The name of the class, it's taken from the description of the concept, and it is the string about, and the value of the string is about, which is about. And the rest is quite simple, because some of those are simply matched exactly, they are matched and returned as an identity function. The only nice thing is this thing that broader is translated as subclass. And all the attributed are linked together and put in at the right place, and then the new class is actually concatenated with the rest of the classes. The result is a result. Then we did a bit massaging by using protégé, because we had basically three ontologies separated, and in particular, we had the fashion objects that were not connected to materials, and to us it was important to have a relation between fashion objects and materials by a relation called made of, that will come in a minute. The question could be, could we have done this by using seduce? Yes, but it was a quite long and boilerplate code, and so we decided to use protégé instead, because one of the goals is also to support protégé. Protégé doesn't use types, so you do manipulations without actually checking types, instead seduce does. Merging is really a word that means a lot of things: reciprocal enrichment, translation of ontologies, merging of heterogeneous ontologies. What we wanted to do is actually to do an example of the third interpretation, which is merging of heterogeneous ontologies. So what we wanted to show was that by using this functional language, we could have simple ontologies and create more complex one to enrich knowledge. In particular, what we did was to integrate the people ontology with the fashion ontology, and in particular, we wanted to find the knowledge representation of a 12th century society and their clothing, and by doing that, we did kind of a broad search of all the garments that were not made of artificial materials, and excluded them. And to do that, we actually used seduce. And yeah, what is nice about this, just a couple of things, and then I'll go to the conclusions. The function made of basically takes an individual, the ontology, and it gives back a sequence of materials. The first individual is matched against an individual which is a named individual with an in the prop with that corresponds to made of, the label we added with protege. So basically what we do is to look for made of, read the material and go to get the other individual that corresponds actually to the material to see if this is labeled artificial or not. And the other one checks if a garment is made completely of artificial or not, or natural material. Then we did other things to integrate information. We had another ontology that had also information on the jobs. So we got, in the end, a very rich ontology where we knew things about how the people lived from the point of view of what they were wearing and what there was their position in the society in a certain age. What we really enjoyed was to see how easy it was to check data transformation instead of checking it by looking at pictures generated by the protege tool. But it's actually a reciprocal support that we wanted to offer. And we hope that this starting point is a contribution to data interoperability. I'm sorry. Thank you.
Maybe Young Kiam, you can start setting up. We have time for questions, for maybe just one question really quick. Viviana, I had one question for you. The first thing that comes to mind when I see this is thinking about schemas and systems for kind of describing the shape of certain documents. And I'm just kind of curious, like, are there other tools, other techniques that you also considered to do this kind of modeling? And good. Let's thank Viviana one more time. So our next talk is an invited talk from Young Kiam. Young Kiam is here in Singapore and has managed to find time to come in to give the talk in his very busy day. So I'm very happy to welcome him up onto the stage to tell us about CakeML. I wanted to mention actually, so CakeML, I think last time it appeared at the ML workshop was maybe a decade ago or more. So very happy to have Young Kiam give us an update on all the things that the CakeML community has been working on over the past 10 years or so. So take it away.
So yeah, thanks for the introduction. So I'm actually not that busy today, but yeah. So anyways, so yeah, in the email that Sam sent to me when he was inviting me, basically he said there hasn't been much CakeML at the workshop. And yeah, indeed, I went back and looked at the proceedings, and the last time it appeared was in 2014, more than 10 years ago, at this workshop, and that was where actually the first CakeML paper appeared at POPO. And specifically, this was the abstract, and at that time, basically, we promised to discuss some plans for new optimizations, new compiler primitives, a new library, and some verified applications. And that's very nice because that's basically what I'm going to talk about today. In the first part of the talk, I'm going to talk about some of the major things that has happened in the CakeML ecosystem over the last 10 years or so. And then the second part, I'll talk about some applications which I have been working on over the last few years. Okay? So before going to that, I just wanted to show this picture, which is the number of lines of proofs and code that's in the CakeML code base, how it's evolved over the last 10 years. Basically, what I'm going to cover is this stuff. So right now, we're at about 750,000 lines of code. But if you include all the auxiliary repositories involved in the CakeML project, we're actually just over 1 million lines of code. So it's a pretty big verified. Thank you. It's a pretty big. Sorry. Hello. Okay. So it's a pretty big verification project.
by, I guess, most standards. Is it? Okay. Okay. So, and what I wanted to say is that the project has been developed collaboratively by many people over the years. So I'm only going to be able to cover the stuff that I'm a little bit more familiar with, and some of the things I'm going to mention are more of the stuff that I've worked on more recently. Okay, so there's also a technical project overview paper, which was in ITP a few years ago, if you're interested in that. Okay, so going into the talk proper, this is sort of the plan. I'll start with an overview of what KML is, and then I'll do a deeper dive into some of the parts, and then I'll talk about its applications in trustworthy automated reasoning. Okay, so yeah, so what was KML in 2014, right, when it first appeared? So it appeared at POPL, and it received just last year the most influential POPL Paper Award. So the main contribution of this paper was to build the first formally verified compiler for a functional programming language, which we called KML, and it compiled from this source language down to x64 via bytecode language. Okay. Now, the verification at the time covered basically the entire compilation process, starting from type inference, parsing and type inference. Both of them proved sound. And more importantly, semantic preservation from the source language all the way down to the machine code model. Okay. And this had to include, for example, a verified big num library, verified garbage collection, and a verified runtime. Okay. One of the very interesting features of the KML compiler is it supports something called verified bootstrapping. So it's able to bootstrap itself and generate a correctness theorem about this bootstrap. And I'll tell you more about this in a few slides. Okay, sorry. And all of this is built using the Hall 4 theorem prover. And what I'll talk about is basically what has happened since this 2014 paper. Okay, so I think really the next step after the POPL workshop, the ML workshop that we attended at POPL, was to redesign and build a new backend for the compiler. Okay, and this was where actually I started getting involved in the project as an undergrad. Okay, so this picture, I'll zoom in a bit later, is actually a view of the compiler as it is today. Okay, we go through 8 intermediate languages, basically sort of a block of front-end languages which are responsible for compiling away some of the more functional features, block of intermediate languages which are responsible for turning a functional intermediate language into an imperative intermediate language, and then we have a bunch of languages at the end which are responsible for target-specific optimizations and code generation. Okay. The KML compiler today is not just targeting x64, it targets actually 5 different compilation targets, and it supports, for example, a foreign function interface, which in the context of our tools allows us to model interaction with the external world as well. Okay, and it's still capable of having compiler bootstrapping. As you can see, the compiler is pretty big, so we're able to actually bootstrap the entire all of these passes. Okay, so zooming in a little bit, right? Starting from the top of the compiler, we have 2 intermediate languages which are responsible for functional level optimizations and compiling away some of the features. Okay, and then we have the block of intermediate languages, sorry, the intermediate layer languages. And I think the most important one here is probably this one in the middle here. It's a small blob here, but actually it represents one of the most complex passes and with correspondingly complex proofs, where essentially we turn abstractly modeled data values into concrete machine words and implement them into the heap. Okay, so moving out of this language is actually where I am the most familiar with. We have an intermediate language which is responsible for low-level compiler optimizations, including, for example, register allocation for target-specific. Register allocation for specific targets. Okay. Now, once we exit out of wordlang, that's where we really start to go down into machine bytes. We have, for example, implementation of the KML stack. So KML manages its own stack, okay, and it also implements its own GC, both verified. Okay, and then we have compilation out of that into a flattened language, right, where we remove all the structured control flow. And finally, one of the things that may be a little bit surprising is that KML actually compiles and assembles itself down to bytes. So the correctness theorem actually applies to at the level of machine bytes. Okay. So I'll talk a little bit more about the targets and actually this CPU later. But you can see here we have both 32-bit and 64-bit targets. And each of these have some form of semantics modeled in the theorem prover itself. Okay. So this gives us a verified compiler, right? Which, you know, in the notation here, basically it compiles some kind of source, kick-ML source program into a target program. And if you successfully do this compilation, what we have shown is that, of course, the semantics is preserved from the source to the target. So this is a little bit simplified, but I'll just go with this for now. Okay. But the kick-ML project as a whole today is able to also offer guarantees about the source semantics, right? So I think since 2014, we have always had a type system or a type inferencer. And of course, the thing that we have formally proved is that, you know, if your program is well typed, then it cannot go wrong. In addition, we have also shown that the type inference is sound and complete with respect to the type system. But beyond that, you know, beyond just type soundness, we also offer tools that allow us to obtain functional correctness guarantees. So we have these tools called the translator. And what these tools are capable of doing is taking as input a Hall function, so a function in the logic of a theorem prover, and automatically generating kick-ML programs. So the base translator actually generates pure programs, and it provably implements the Hall function. And the monadic version of this translator actually generates stateful kick-ML programs via reflection of the monad. Okay, and this requires you to write a higher order logic function within a certain monad. Okay. So as you can see, this is sort of like adding a little bit more state. And if you really want to go for sort of a full stateful program using arrays, exceptions, and whatnot, then we actually also have a formal framework for doing separation logic style reasoning based on characteristic formulas. And this is verified to be sound against kick-ML semantics. Okay. What's important is that actually all of these tools are verified give us verification guarantees about the source semantics, but the guarantees actually compose with the compiler correctness theorem. So we can actually obtain functional correctness guarantees about the generated machine code at the end. Okay. And that's actually what allows us to obtain what we call a verified, obtain a verified bootstrapped compiler, right? So I just wanted to show this a little bit of intuition for this. Right, so the kick-ML compiler itself is actually defined as a bunch of logical functions in the theorem prover called Hall. Okay, it looks a little bit like this, I mean, simplified. Okay, and we proved the theorem that I showed just now, which is semantic preservation from the source to the target. Okay, now what's interesting is we have the translation mechanism, and what we can do is we can take the translation mechanism and apply it to the compilation function itself. Okay, and this is going to generate us a kick-ML program, right, whose semantics is equal to the compilation function. Okay, this is through the translation. Okay, and now one of the things that you can do in many provers today, including Hall 4, is you can take this compilation function and apply it to the AST of itself generated by the compiler, sorry, by the translator, and you can sort of run this inside the theorem prover and obtain a theorem that says the compile of this piece of AST is equals to some machine bytes, okay? And this is basically the byte level implementation of the compiler, okay? And now if you put these three theorems together, what you get effectively is that the semantics of the machine bytes actually implements the compiler itself, okay? Which, yeah, if you look at these chains together. So this sequence of bytes is what we call the verified bootstrap compiler binary, okay? So maybe I'll give you a few seconds to look through the sequence of things. Yeah.
Are all these pieces put together in a Hall, or?
Yes. Yeah. So all of these are proved as theorems in Hall, and this thing is also proved as a theorem in Hall.
Yeah, but they're put together. Okay.
Yeah, it's all in Hall, and we have this theorem in Hall. Yeah. Yeah. Thanks for the question. Okay. So yeah. So of course, in reality, the bootstrap is not as sort of clean as what I showed on the previous slide. So most of the equations, equalities I showed on the previous slides are actually some kind of relations. And well, as we expanded the compiler to this whole thing, we actually needed to also expand the kind of things, we expanded the compiler, also needed to expand the kind of things that a source language has so that we can actually bootstrap the compiler. But the good thing is actually we are able to bootstrap it, which means that our source language is sufficiently expressive to, for example, support the word level manipulations that you need to do assembly. Okay. Some other details, for example, carrying out the translation, you need to be a little bit more careful. For example, for some of the compilation passes, you really want to, for example, make sure you use some stateful features so that it actually runs okay in speed, right? It doesn't take forever to compile. And the full bootstrap is actually very expensive. We actually have nowadays regression infrastructure that runs for overnight, maybe about a day to actually finish the whole bootstrap. Okay, it used to be more than a day. It used to be like 2 or 3 days, but nowadays it's a day. Okay, so that's the compiler bootstrap. But if we take a step back, the bootstrapping is really in an instance of what we call binary code extraction. And what that means is we are able, inside a theorem prover, to verify software all the way down to their machine code implementation. And this is verified against the machine code semantics. Okay, and this actually, from the perspective of an ITP, eliminates part of the trusted base. So for example, we don't need to trust code export from an ITP. We don't need to trust, of course, an unverified external compiler. Okay, so I'll talk a little bit about binary code verified applications in the later part of the talk. Okay, so that's a quick overview. And now I want to sort of dive a little bit deeper into some of the parts. I think I've chosen to start from the top and go down. So, okay, so in terms of verification tools, I already mentioned the translator and the characteristic formula. So what does the process look like? So to use the KKML translator and monetic translator, what we do is write a Hall function, so a higher order logic function. And this is also known as a shallow embedding. We write it in a theorem prover. We prove some properties about this function. Okay, and then we call the translation mechanism to automatically generate a pure, or in some cases, a stateful KKML function. And it automatically shows that this KKML function's semantics implements the given Hall function. Okay, so we also have, as I said, if you want to go beyond what the translator and monetic translator are able to give, we also have something called characteristic formulas, and this is a framework that essentially allows us to do separation logic style reasoning over KKML programs. And what it means is we can write so-called deeply embedded KKML inside the theorem prover, and then again state and proof properties, but this time about the deep embedding. And what it means is we need to use sort of customized tactics to reason about CF specifications, so characteristic formula specifications. So one of the things with KKML's CF framework, for example, is it supports essentially all of the imperative features that you can find inside KKML, state exceptions, talking about the FFI, and it even supports reasoning about diverging programs, so reasoning about infinite traces that are generated by divergent programs. Okay, so I just wanted to mention, well, one of the things that's a little bit of a drawback right now is that the automation we have isn't that great. It'd be nice to have a better library for this. Okay, what's important actually is that these two things are compatible. What that means is in a typical verified application for KKML, what we would do is kind of start by writing everything purely, right? And then using the translator to automatically generate KKML. And then as we sort of profile and go along the way, we find that, well, maybe some of the functions really should use some form of actual state. And then we would actually swap out that function for a CF verified function, okay? And this is maybe a little bit of unfamiliar workflow, but what it allows us to do is really sort of use this part selectively to optimize whatever application we're trying to build in a verified way, okay? So I have some of these boxes here, which are some of the wish lists that I have. As I mentioned, it would be nice to have a more streamlined program verification framework for KKML, including, for example, speeding up and automating our separation logic libraries. Okay, so going a little bit down into the language front ends. So besides KickML, what we have done is also built on the compiler backend as a backend for other languages, right? So one of the first projects I think was this choreographic language. So it's a language for describing distributed computations, right? And what has been done is, again, verified compilation into sort of a group of KickML processes communicating via the FFI. This is also, this compilation down into the instances is verified as well. Right, another project was to provide a Haskell-like front end for KickML, including supporting lazy call by need semantics, okay, with monadic reflection. So you can see this is a picture I took from the paper. It basically starts from a Haskell-like front end and actually compiles into KickML source. So project. So that's another project called Pancake coming out from the folks in Australia. This was a system-oriented programming language, and it actually targets some of the lower-level languages in KickML. What it does is actually compiles into the middle end of the, the back end of the KickML, the lower end of the KickML compiler, which is then responsible for doing things like register allocation and target-specific optimizations. Okay, so there are a few other front ends. Most recently, we built one for Daphne, including a verified compiler and verified VCG. And there's going to be, there's also a front end for Scheme with support for first-class continuations, and there's going to be a talk by Pascal, I think, later today. Okay, so I think what's interesting about building these new language front ends is, of course, the compiler verification question, but also, there's also the problem of can we build associated optimizations in the compiler backend in order to speed up some of these applications, and at the same time also, of course, speed up other applications as well. Okay, so going all the way down to the end of the compiler. So as I said, we have both 32-bit and 64-bit ISA targets. Okay, all of them are implemented essentially by first compiling to a generic assembly language and then encoding this assembly language into the respective backends. Okay, all of these, well, we have essentially verified assembly for all of these targets. But beyond that, some interesting things that has happened over the last few years. One of them is our ARM8 target. So we call our ARM8 target semantics actually authoritative because it's verified against ARM's officially released ISA model. So we have a compilation theorem that says the KickML compiler actually correctly preserves semantics down to this particular model. Okay. We also have this Silver ISA over here, which was a project on building a proof of concept piece of hardware, right, which is verified down to its Verilog semantics. And also we have a compilation theorem that goes down all the way to verified Verilog. Okay. So in future work, some of my students and others are working on, for example, broadening the class of targets that we have, in particular WebAssembly. So verified compilation, I think, from slightly above here down into WebAssembly. And one of the things that I think would be interesting is to revisit this design decision to have generic assembly layer over here, because that really blocks us from using some of the more specific instructions that might be available on some ISAs. So we do want to kind of revisit this and see if we could maybe tweak this a little bit and to support more instructions, let's say on x64. Yep, sorry, to use more instructions on x64. Okay, so one more thing that I haven't mentioned so far is that actually the compiler that I've shown so far is really, you could consider it the third iteration of the compiler, because the thing that we have added most recently is what we are calling dynamic evaluation or computation. And what that means is in the source of KickML as it is today, we have an operator called eval. Right? And what it does is at runtime, if you give this eval a value which happens to decode into KickML abstract syntax, right, it will actually run the bootstrap compiler on this piece of syntax, and then it will write the compiled bytes in your memory, the instruction, in your instruction memory. You'll write write those bytes into there, and then it will jump to those installed bytes and actually execute it. So in other words, we can actually install new code at runtime, right? And this allows us to, I guess, rebuild a verified read, eval, print loop. And more importantly, actually, this actually fulfilled one of the really early goals of the KCaml project, which was to build a verified interactive theorem prover, which we called Candle, which is built on top of KCaml. Okay, so I just have a quick demo of this. So actually, oh, I didn't realize it's going to be too small. Let's see. Make it, let's see. Okay, so by default, KCaml, well, so this is compiling the compiler itself, and then by default, KCaml is actually able to compile programs that look like this. So this is just a factorial program, which I actually asked ChatGPT to generate, but I mean, I could have written it myself, but anyway. So you can see actually on this line, this is the KCaml bootstrap compiler called on the factorial program, and it generates assembled bytes. And yeah, it actually runs and generates the factorial. But actually what you can also do is, let me see if I prepared so what you can also do is actually run KCaml in REPL mode, right? And in this mode, you can actually interact with it. So I'm hoping you can see this. Yeah, so you can actually interact with it. And this, what's happening behind the scenes is actually, as I said, taking the code, parsing it, turning it into KCaml abstract syntax, running the bootstrap compiler on it, taking the bytes, putting it in the memory, and then jumping to those bytes and running it, right? So that's what's happening here. And in fact, what you can do is, let's see, copy this, and then you can do that, or like that, or yeah. So that's what we can do with the REPL. Okay. So as I've written here, one of the drawbacks that we have right now is that because we have to do this thing where we write into instruction memory, we're limited to systems that don't have write exo execute at the moment. So that basically rules out all Mac OSs. But we're working to lift this limit as well. Okay. So for the rest of my talk, I'll be talking a little bit more about an application that I've been working on using KCaml for the last few years. And this is in what's called, I guess, trustworthy automated reasoning. Okay, so what does that mean, right? So here's the question. If you have an automated reasoning tool, right, you give it some verification problem. Let's say it's a set solver and you give it a CNF. If it's an SMT solver, you give it a problem in SMT-lit, and so on, right? And you expect this automated reasoning tool, in most cases, to give you some kind of result, right? Whether your problem is unsatisfiable, whether there's a model, and maybe it prints a model out, okay? But the question is, how do we trust the correctness of this result, right? So for satisfiable cases, typically you get a solution as well. And in that case, it's pretty easy to check the answer. Just make sure it satisfies all of your constraints. But in other cases, we are interested also in, for example, unset results, right? Which would correspond to, for example, your circuit doesn't have any counterexamples, your program doesn't have any, your specification doesn't have any counterexamples. And in those cases, what we're interested in is for the automated reasoning tool to be able to justify its answer beyond just saying that, well, there are no counterexamples. Right? So in the automated reasoning community, this is a topic that has got a lot of attention in the last few years to ensure that their tools are actually sound. And so the approach that's been taken up by the community is something called certifying algorithms. Okay, and what this is about is essentially many automated reasoning tools today are able to generate something called a proof or a proof certificate. And this is a proof of, for example, unsatisfiability, which you can then feed together with the original verification problem into something called a proof checker, which is able to check the correctness of this certificate in an independent way. Okay, so this is the sort of general setup, okay? And as you can see in this picture over here, as you can see this picture over here, really what this does is it reduces the trusted base from having to trust this complex automated reasoning solver to just the code base of this proof checker, okay? And what's perhaps more interesting for verification is that this proof checker itself, it can be formally verified. Oh. Hello? Am I supposed to use this? Oh, okay. Okay, so this proof checker itself, it can be formally verified. Okay, in particular, it can be formally verified using CakeML. Okay, and that's what I'm going to talk about. And so what I'll do is I'll tell you about what we have been doing in the set scenario. So we have a set solver over here. And as I said, a set solver is able to either produce a satisfiable result or an unset result. Okay, and in the satisfiable case, you get a satisfying assignment. All you need to do is to plug it into your formula and check that it evaluates the true. But in the case where you get an unset answer, most modern set solvers today are able to generate something called an unset proof, which you can feed into an unset proof checker. Okay, and it looks a little bit like this, right? So if you give a set solver a problem, this is the standard input format in conjunctive Boolean formula in conjunctive normal form. Okay, what the set solver will print out is a sort of a sequence of numbers that look like this, and this is the file that kind of goes into your proof checker, where you can tell whether it's, and then the proof checker is responsible for saying whether it's valid or not. Okay. Now this started being used in the set community about 2014. Okay, and one of the questions immediately got was, how can we further enhance the trust in this proof checker? Okay, and I think the verification community really stepped in at that time. So around 2017, people figured out that, well, if you just made the solver print out a little bit more information, you can actually have a formally verified proof checker. And at the time in 2017, there were a bunch of different proof checkers which were able to check such proofs. Okay, so we can skip these details, but so just to give a little bit of a summary and a timeline, every year the world's best set solvers compete at this international set competition. Okay, so since 2014, proofs have been mandatory for all set solvers participating in the competition. Okay, now since 2017, not just proofs, but you also want the proofs to be checked by a verified proof checker. And 2021 was where CakeML started coming in. So in 2021, the formally verified proof checker that was used in the set competition was built using CakeML. Okay, since 2023, actually a set competition decided to say, we're going to allow you to use any proof format that you want as long as you can provide us with a verified proof checker. So we actually provided an alternative format as well. Another thing also happened in 2023, which is that one of the best open source set solvers out there, called Cadico, it started to be able to stream these proofs, right? And in particular, it could stream the proofs directly into the CakeML-based proof checker. And what that means today for set solving is that verified proof checking, which helps to improve trust in set solvers, can be done for free, like actually free. So, so the proofs can actually be output and checked with negligible cost to set solvers. So I wanted to show this in action. So yeah, so what I'm running here is actually the set solver that I mentioned. And what it's doing is I've passed it a CNF, which is a input problem, and what it's doing is going off and solving that CNF. All right, eventually it will show unset, but this takes about 2 minutes. Okay, but what's happening here is that actually, if you can see in my top over here, right, Cadico is running. This is a set solver, and running next to it is actually the proof checker. And what's happening is that this thing is writing straight to a pipe that goes into the proof checker. So the proof checking is happening directly at runtime for the solver. And of course, there's a verified soundness theorem for CakeLPR, if I didn't mention that. So anyway, this will take a few more seconds. I'll come back to it. But that's what's happening. And yeah, well, actually. So I think every talk nowadays has to have a slide about AI. So this is my slide about AI. So something very interesting happened in the 2025 SAT competition, actually. So it was won by this SAT solver, AE KeySat MAB. And well, you don't really know what these means, but AE was their framework for using LLMs to tune the implementation and heuristics of SAT solver. So this was won by an AI-tuned SAT solver this year. And actually, it won by a significant margin over the second place solver this year, right? So I think what's interesting is that these results were actually cross-checked by verified proof checkers. Another recent paper, which I think is not yet refereed, claimed to even surpass this solver in performance, right? So, and here they actually used AI-based agents to autonomously evolve entire SAT solver repository, not just tuning heuristics. So in the paper, they actually mentioned that proof checking was used to make sure that the generated solvers were actually doing the right thing, right? So for me, I mean, as I said, this is not refereed result. I'm not saying that it's definitely correct, but I think it would be really interesting to see what happens at the next year's SAT competition, if anyone's interested in that, okay? But what I wanted to say is that this approach of certifying algorithms and building efficient verified proof checkers seems to be a nice way for us to make sure, at least in these domains, that AI-generated software behaves as intended. Okay, so, right, so going back to the solving, so what you can see is that the solver finished up. I think it decided that the problem is actually unset. And at the same time, the KML verified proof checker also said it's unset. And well, I mean, you can't see it right now, but actually this probably happened just a split second after this thing finished. Okay, so proof checking is really for free in the SAT domain nowadays. Okay, so of course we have gone way beyond SAT today. We actually have a range of formally verified proof checkers in KML. For example, for SAT solvers and their extensions, we have proof checkers for approximate and exact model counting, for 0-1 ILP, for various other combinatorial solvers. We have one for MIP. Yeah, I mean, if anyone's interested, we would be happy to build more verified checkers for new automated reasoning tools. Okay, and all of these tools that are shown over here, they have been verified sound to the machine code implementation using the binary code extraction mechanism that I've talked about earlier, including both to x64 and to the authoritative ARM8 semantics. Okay, so I think this has been a very fruitful collaboration between some of us in the KML community with the automated reasoning community. Okay, so what's there? So one of the points I wanted to make with my talk title as well was the back again part. So I think this process of building new verified proof checkers in together with the automated reasoning community has really given us also insights into how we can improve the performance of KML generated applications and also tooling. So for example, one of the things that I already mentioned earlier is, can we streamline our verification tooling? And can we improve the prototyping, benchmarking, profiling techniques that we have for KML applications? Along the way of building these proof checkers, we have, of course, developed new libraries, which allow us to, for example, do streaming I/O support, hash tables for some of these proof checking algorithms. One of the things that, at least, I don't know if you think this is nice or not, but one of the things that we can do, because we are in full control of the compiler, we can introduce new primitives that we want, that we need for the proof checkers, and we can actually efficiently support verified compilation for these primitives all the way down to machine code. One of the big things that we are hoping to build soon is a verified big num arithmetic library. Sorry, we already have one, but we want to improve it so that we can better support mixed integer programming proof checking. Okay, and of course, I mean, many of these involve verifying new compiler optimizations, low-level code generation optimizations, and of course, we are always interested in expanding KML verified proof checking to other domains as well. Okay, so just to summarize, I would say the KML ecosystem has grown very substantially over the last 10 years since we appeared at the workshop. but there remains many more questions to be tackled. And at least for what I'm working on, I think KML has had a really nice symbiotic relationship with automated reasoning. And I think we are going to continue that for the next few years. Okay, so just wanted to say we're always looking for new contributors, so please feel free to approach me if you're interested. Thank you.
So time for questions. If you want to ask a question to Young Kyum, just come on up.
Sorry, Shagari. I've been wondering because I have the impression that all you presented has been created anew for KKML, and I understand why you need to do that because you want to prove everything, so you have to build it and prove it simultaneously. But were there also attempts, since you're using ML, to well, compile some software with KKML and even maybe try to prove something about it? Some existing software? Well, I suppose Isabelle would be too big, but...
Right. So in terms of existing software, we have tried to, I mean, one of the things that we're maybe a bit lacking is in terms of benchmarking. We have tried to actually benchmark the KML compiler on existing benchmark. But in terms of verifying existing code, I don't think we have tried that at all, actually. Most of our code is basically written from scratch and for verification. Thank you.
Hi, I'm Cesar from MPI. So I think my question is related to the previous question.
Right.
So did you try, I don't know, to compile some of the libraries of OCaml, and like how much does it support, how expressive is KKML to compile existing OCaml code?
Right, so what we do have, I don't think we have tried like OCaml code, but what we have tried is actually, so what I mentioned just now is that we not only have a verified REPL, we actually have a verified implementation of an interactive theorem prover called Candle. And Candle is actually, the way we supported it was we made a front end that resembles OCaml. So Candle is actually a clone of Howlite, if you know that theorem prover. So Howlite is a theorem prover which is actually written in OCaml, a slight variant of OCaml syntax, but actually this tool was able to handle quite a large fragment of the Howlite libraries as is, almost as is.
Okay.
Yeah.
But my impression was that the idea to have a verified compiler for ML is to kind of, not necessarily, I mean, it's twofold, right? I mean, on one side you can verify code in a proof assistant, but then you can also just compile the code and have the guarantee that the compilation is verified.
Yes.
Right, so one can compile code without necessarily verifying the code. So you're saying that KKML doesn't really, is not able to necessarily compile OCaml and...
well, it wouldn't be able to, right now I don't think it would be able to support the full range of language features that we have in OCaml. So I would say the language features that we have right now are, we are sort of adding them as we build things. So I mean, what we have is enough to support the applications that we have built. Yeah.
Thank you.
One of the aspects of KML that I've always been fascinated by is the proofs, in some sense, of efficiency. I mean, it's not really efficiency, maybe, but like a bound, right? Maybe I need to be able to prove that within a certain space bound, the executable will actually complete and succeed in its execution. And I'm just kind of curious, is there more to do there, or are the existing results you have completely sufficient for all of the work that's been done in KML? I don't know, maybe you can just say a bit about that aspect of the project.
Yeah, so I think it's like slightly hidden here. So we do have a cost semantics for KML as well, okay? But we don't actually prove the cost bounds for most of our applications. What we have actually in the compiler correctness theorem, which I showed as a lie over here, is that actually the source semantics, the target semantics will behave exactly like the source, except if it runs out of memory. It will actually simulate a prefix of the source only, because of course the source semantics has unbounded with integers, and the target semantics has finite memory. We are going down to actual a very concrete machine model, right? So we don't have infinite memory. So the answer to your question is that, yeah, we don't, we have a coarse semantics, which we have used for some examples, but I would say, I mean, if one were to seriously look at this, I think we would, for example, want to have more automation for proving the cost bounds for new programs. Right? So another thing to mention is that actually in the applications that I have in the applications in trustworthy automated reasoning, sort of what you want at the end of the day is a guarantee that if you print unset, then the problem was actually unset. And so we haven't really needed this bounds because, I mean, if it runs out of memory, it runs out of memory. So you don't get unset guarantee, but in terms of soundness, it's still sound. So yeah. Thank you.
the OCaml language with a language people tend to do a competition with, which is Haskell. Both of them are functional languages. Both of them are statically typed. But on one side, OCaml has a module system, which Haskell hasn't. And on the other side, Haskell has type classes, which OCaml hasn't. But on both sides, the communities want each other feature, and we can see on various forums people talking about emulating the other feature with the one they have. And this shows like there's kind of frustration in the communities of not having both functionalities at the same time, but the problem is they're not compatible due to various problems. And there has been a proposal 10 years ago of emulating type classes with implicit module arguments, such a way a bit Scala-like, and this will be an idea to solve this problem. This proposal has been done by Leo White, Frederick Bourg, and Jeremy Yallop 10 years ago at the ML workshop called Module Implicit. So the idea is we have a module system with the way it is now in various languages. So you have signatures and you can define various modules and functors, and you can declare them as implicit. For example, here I define a signature for printing a type. And then you can define a function with an argument you label as implicit, and this is a module argument. Such as when after you use this function, you can omit the argument and actually have an equivalent of type classes. So here, you're for printing a list of integers. But the good thing is you can also instantiate the argument by hand in opposition to type classes, so you can do more things, because it's an implicit argument and not a real type class. So this proposal has been done 10 years ago with an initial prototype, but it was more a proof of concept. Since then, over the last 2 years, there has been an implementation of module explicits, so it is the elaboration language for module implicits. Then comes the elaboration. So you need to infer the module expression, and this is what I'm going to present you today, because there has been, over the last year, an implementation of module implicit and a formalization of it. And in the future, we'll still need to fix the problem of the interaction between type inference and elaboration of module expression. So for the elaboration, the idea is to add to the language a new feature which is the idea of elaborating module expressions. So we add a new construct, underscore, which is always followed by a signature. And then we have a set of modules, including functors, that we can use for synthesis and, of course, for related signature. And then from this, we're able to elaborate the whole module expression with only applications. The reason we use application is because it's easier to infer. And so in this case, we're going to infer the module defining sets for pairs of Boolean and list of integers. This can be quite complicated to write by hand, but we're able to infer it fully. But in the end, we still have a set of constraints we want for the solution. We want it to be sound. We want to infer a well-typed solution. We want the inference to be deterministic, to have a deterministic semantic in the end, and not have a different behavior for a program at each compilation time. And we will hope that our inference is also complete and find all possible solutions, but sadly we will see that's not the case. So for soundness, the idea is we're inferring module expression, and we're just having a subset of the whole typing rules for modules, only applications of modules. And this gives us a small set of rules, and with that we know that we're sound, because we can infer a module only if it has a valid type for the asked signature. For determinism, we just add the constraint that a solution is valid only if all possible solutions are optionally equivalent to the one we take as the valid solution. The fact that we want something optionally equivalent is the biggest relationship we can have. We can just take a smaller restriction and we don't lose determinism. We just have a few cases that will be rejected that could have been accepted. For example, in OCaml, we want to have an observability equivalence inference just based on the location of the definitions and not look at the exact code. Then for completeness. So I'm going to take a small example where I want to infer a module defining comparison on list of integers. So for this, I create a small search for the signature. And I can see that I only have one solution for this, which is calling the list comparison functor on an argument of signature of comparison on list of integers. Then I can apply my same functor once again, and then I only have one solution, which is the module int. So I've done an inference. But what happens if I take a bit more complex example? So I'll take a signature t, which can be abstract, and I also take a functor from t to t. And if I ask for a module of signature t, then I have, which is applying the loop functor to a signature t, which can then be inferred as applying the loop functor to a signature t. And this starts to pose a bit of problem because we're not progressing. And this might cause a divergence in the compiler, so the compiler rejects it by saying that, oh, it's not able to guarantee that the search is going to terminate, so it's stopping the search. And so this example is rejected. Whereas we could have used fixed point analysis, saying that there was only one solution, or just saying there was no solution because we don't have an initial way of building a module of type T. So this is a bit of a completeness problem. But for the termination guarantee, how do we check this? So we need a termination criteria, and the idea is to define partial order on signatures and ensuring that all recursive calls are strictly decreasing for that partial order, and we also want this order to be a well-founded order, so that the search is going to terminate. We also want a few properties for this order. The idea we want to know that comparing integers is a smaller signature than comparing list of integers. The idea is that it's really likely that when searching a list comparison on list of integers, we will recursively reach integers. So we want to consider that this case is strictly decreasing, otherwise many examples will get rejected. In the same way, we want to say that int list is smaller than any type, because specifying type might be progressing in the search. And so to build such an order, the idea is we define a metric on types, and we use the order on ordinals. The idea is that if we have a static type with a certain depth, we define the metric as the depth of the type. And if the type is not static and contains type variables, we take the depth times omega as the depth, and this creates the order that preserves the rules presented of. And then this defines an order on one type, and a signature contains many types. So we can compare all types of signatures together and use an order on those, such as punktwise or lexicographic, depending on what we want. The whole search is parameterized on this termination criteria, so depending on what we want, we can choose a different one. So we said that all recursive calls must be decreasing. So I'm going to take a new example with, once again, the signature show for printing a type, and a functor from list that says that if I'm able to print a list of type T, then I will be able to print the type T by just printing a singleton. And then I'm giving also a module that explains to me how to print a list of integers. And then I want to print integers. So it's a singleton, a singleton, a singleton of the integer. It's easy. But if I'm doing this search, I need to start by calling the fromList functor on printing of list of integer. And this fails because we're not decreasing. Int list is not smarter than int. So this is an incompleteness problem that comes from the termination criteria. However, we deem that such examples are not likely, so we don't care that much about it. And just in case somebody happened to stumble upon this incompleteness problem, there's still the solution of writing by hand the modular expression compared to type classes where you cannot have any solution to your problem if the inference fails. So another problem that arises with inference is the case of functor with multiple arguments. So I'm going to take a functor f, which takes two arguments, an argument a that defines arithmetic on a type, and I have many solutions for this argument. But I also have a second argument s, which defines sets on the same type, and I know which kind of set it is because the return type of functor constrains this type. And if I try to infer the first argument first, I will fail because I have two solutions. On the other side, if I start by the second argument, I only have one solution, I can infer it. This gives me additional constraint to infer the first argument. So in this case, I have one order that is valid, while the other will get rejected by the type checker. And so I don't want the user to take that into account when writing their functors for the order in which they write the argument. So we don't want to constrain the inference of the arguments with a specific order. So we just said that if I have a functor with two arguments, fixing left to right or right to left, this poses an expressivity problem because the user cannot write the program they want, even if they're sound, because the inference is not strong enough. A way around this problem will be to do multiple passes. So I have a functor with two arguments, I can try to infer argument 1 and argument 2, and then if I have inferred at least one of both, but not the other, I can try once again to infer the argument that has not been inferred with a new information. However, this requires me to do 3 inferences for only 2 arguments. And this poses a complexity problem because I'm quadratic. Another guess will be to infer all pairs of arguments possible. So I look at all the solutions for 1, all the solutions for 2, and I try to match them together. But this poses also a complexity problem. I'm once again quadratic. So the solution we propose is to have a dynamic inference with incremental search. So for this, we define a state of the search, which contains a targeted signature, the set of currently valid solutions, an explored space of modules that can be looked on to find more solutions, a focusing point, which is the module we're actually looking at to know if it's a valid version or not, and also a name, which is a typing artifact. And with those, we then have a set of reduction rules, which can go from a state to another one with various constraints and conditions. However, this state has many things in common. For example, the context, the name, and the targeted signature never change in one direction, so we just omit them in the rule. And the set of constraints that comes from a context, we're going to move it to the size for presentation reasons. So I'll now take another example to explain to you how we use this state and the reduction rules. So if I have a signature S1, which defines a type T1, and one module M1, which is of this signature, and it's the only instance for that signature. I then define a second module type, S2, and 2 modules for this signature with different types. And I have a targeted signature sol and a functor that will generate this module type with a call feature and takes 2 arguments, x and y. Both define the same type, but x is of signature S2, which has 2 solutions, and y is of signature S1, which has only 1 solution. And then I'm going to start a search to look for my signature with a call feature. So, and doing this in the context where I have all the modules presented above. So I have my initial state for search, where I'm not looking at any modules, and I also have a set of modules in the context that I can look at. And have a first role as focus, which allows me to take a module from the database and start to look at it by moving it into the focusing point. So I can use this role to do a reduction on the state. But then my module M1 defines a type T1 when SL requires a cool feature that M1 does not contain. So I can use another role which drops away M1 to forget about it and be able to continue the search with more interesting modules. So I can just forget about M1. In the same way, M2A also is not valid for the targeted signature, so I can use the two rules presented before to forget about it. The same for M2B, and then I can start looking at F2 implies 1. So now I'm looking at F2 implies 1. So this module is a functor. So to infer that this functor is actually a valid solution, I will need to infer its argument. So I can use another rule that opens the application by creating a search for the two recursive arguments. In those search, so if I take the example of y, I still have the name y, which is typing artifact, and the targeted signature. But this inference happens in the context where I have x, because there is a telescope in functor arguments, and the first argument is known by the second argument. So I have a local extension of a context. I also have the initial state of a search, where I'm not looking at anybody, I haven't found any solution, and I have a set of modules from the context that I can look at. And also, for termination criteria, I also know on which signature the functor was called, so that all new calls to this functor will ensure that they are strictly decreasing. So with this state, I can start to try and infer the argument. For this, I have a rule saying that if I do reduction in one of the arguments, I can apply this reduction on the whole. And I can then do a huge amount of reduction to infer all possible solution for x, which is M2A, M and 2B. But then I have two solutions that are not the same, and you could say that the search has failed because I have an ambiguity. But we also have a second argument, so we're going to look so this creates a new state for first argument. Then we can look at the second argument and use once again our rules to reduce it to only one solution, which is M1. And M1 also defines that T2 is of type int because we have a constraint between the signature of y and the signature of x. And this becomes the new state of our search. So we have this information inside the argument y that the type T2 in x must be int. But this is local to the argument. But we have inferred this argument fully, meaning that if we have an actual solution for this functor, we need to have this constraint to be valid. So we can extract this constraint from the inferred argument to move it to the application because it's a whole rule for the application. So we can do a reduction by lifting the constraint out of this argument and having available for more people. And then we have this new constraint, which X is able to look at. So we can use it to reject the solution M2B because it defines that T2 is low. And because both constraints are incompatible, this means that this solution is invalid and we must forget about it using the rule SPLASH'25. So we can forget about it and have only one solution for X. Meaning that now we only have one solution for both arguments. The solution for X is M2A, the solution for Y is M1. Meaning that we have fully inferred all arguments for this functor application, and that we can solve the solution by extracting all the solution from each argument and building a modular expression from it. And now we have a valid solution, which is the functor applied to those arguments that have been inferred. And this is the solution from the search. But in practice, we have a few subtleties with the implementation because we want to be efficient. And we need to have several optimizations to quickly filter out subtyping failures. So first of all, we have a constant time selection of all modules implementing the most significant recurred field by just accessing the database. Then we have a constant time shallow subtyping approximation by only looking at the field names. We are not going more inside the signature to look at the type that are defined. We just check that all the names we want are actually inside the signature. And then we can do a quick structural approximation of subtyping to reject the last failing example that have passed the filters that happened before actually doing the final subtyping, which is much more costly, but at least we hope that we don't do it too much because most invalid examples will already have been rejected. So, as a takeaway, so we have a formalization and an implementation of implicit modules that is incomplete because we have a problem of decidability of when we're terminating, so we don't have every example that are accepted. But it is designed to be expressive in practice by accepting lots of examples and not adding any constraint of the order of the argument synthesis. And we also avoid word duplication and backtracking to be efficient. This framework has been also designed to be customizable. We can modify the termination check, but we can also add new reduction rules to cover a few more cases. And the elaboration of modular expression is much more complex than for type classes inference, and this is why we need such a huge set of rules to be able to infer things efficiently. But we still have the problem of fixing the interaction with a core language in order to be able to have a mechanism that proudly say that it emulates type classes in a modular language. Do you have any questions?
Thank you, Samuel. We have about 5 minutes for questions, so please come up to the mic.
Hey, thank you for this. I'm very excited to get modular implicits in OKML, so thank you for your work here. I'm curious if you could talk a little bit about what you think the scoping rules should be for like what implicit modules and functors should be like in the search space, because I know that like in the world of Scala, for example, this is something that frequently causes people headaches.
Yeah, so one thing that's extremely important for modular implicit is that compared to Scala implicits, is that if we have multiple solutions, if there are multiple, we reject the example. Whereas in the opposite, Scala, if they have multiple solutions, they take the best one. After what we put inside the context, that's, I think, more global decision, but we have also still the problem of if we add too many things, it becomes much more difficult to understand what the program is doing. But modules have much more structure than core language values. Like we can actually give a name to a field, and the name contains information, not just a type.
Thank you.
Does this respond to a question?
Yeah, thanks.
Thanks for the talk. So I was wondering how the search procedure compares with Scala, and specifically regarding the termination criterion, because Scala has its own criterion that seems to work well enough. You have something that looks more complex. I think in Scala, you just make sure that the size of the query type doesn't increase, and that's pretty much it as far as I know.
The thing they have in Scala is you infer type, and so the type might be just decreasing. Whereas with modular implicits, we're inferring a signature, and we can just change fully from one signature to the other, like completely switching from a problem to the other, saying, oh, I wanted to infer arithmetic, but I realized that I can just infer the whole arithmetic if I have another property. And the question is, do we actually want to compare both properties? And do we want to, when we're comparing two signatures, we have a whole set of types inside a signature. And so we can, do we consider that all types in the signature have the same weight for termination?
I'm not sure because I'm not sure how it compares, but it would be useful to have a proper comparison. And regarding the scoping question, I guess what I wanted to ask is, where do you look for these functors? Is it just everything that's in scope, or do you look at things that are not in scope, like that things associated with the types?
We only look at the things that are in scope, but when adding something in scope, we ask for an annotation saying, can we use it as implicit? So we don't take all the functors. We only take the functors in scope that have been labeled as usable.
Manually import all the functors that could participate in the resolution?
Yes. Yes, or opening libraries that define them, but in the library they say, oh, this one, you can use it as such.
I think we have time for one more question. Well, maybe the next speaker can already come up, and I want to invite all of you to join us here in the front rows if you want to sit down. There's still a bunch of space available.
Yeah, my question is about, so you have this restriction that there must be a unique solution, right? Which seems to me to have the implication that you lose the weakening property of the type system. So meaning that a program that is well-typed could suddenly become ill-typed by adding some definition to it that is not actually, it doesn't actually depend upon. Do you consider that a practical problem from like a compositionality or software engineering perspective, or are you just okay with
that? It's indeed a problem we know that exists. We hope that in most cases we have multiple instances of signatures for various type. And so we don't happen to have many cases where we infer type based on the fact that there was only one solution, and that it's more that we have only one type that is valid, and from this we're able to infer the solution.
Okay.
But
thanks.
in practice, that's actually a problem.
Okay, thanks.
Let's thank the speaker again. Language for extended pattern matching and binding Boolean expressions from Arthur Chagaro and Yanni Levki.
Thank you for the presentation. So, hello everyone. I'm Yanni Levki, a PhD student at INRIA Strasbourg.
Well explained. Merci.
Ça va, ça allait,
the mic away from the...
Sure.
No, it's not this issue. You can take it off if you want.
Sure.
But just keep the mic away from the speaker. Okay.
Sorry. Anyway, so I'm a PhD student at the University of Strasbourg. Advised by Arthur Chagaro, and I'm going to present some unification process for pattern matching called a core language for extended pattern matching and binding Boolean expressions. So, when talking about pattern matching, we have to speak into the microphone. So, in the microphone, because sure, okay. Tell me if there is any interference. Sure, okay. So pattern matching is very old as ML actually. So got created in the 70s. We have a lot of improvement along the years. So we had some exhaustiveness checking, efficient computation scheme, first-class patterns, views and active patterns from Haskell and F#. At the time, maybe we thought that all the problems were solved, but in fact they were not, or there was no consensus on how to unify pattern matching. So more recently, we have the if-let construct from Rust, which allows for flowing bindings along the condition. And very recently, we had a work from Liu Cheng and Lionel Parot called Ultimate Conditional Syntax, which presents unifying syntax for pattern matching. Our work aims at pretty much the same thing, trying to provide a yet even slightly simpler syntax with the semantics and typing rules to go with it. So first, I will present a small two features that we would like to have in pattern matching that is not in every language. First is what we call smart deconstructors, or views for Haskell people, or active patterns for F# people. So say you are a compiler creator, crazy, right? And you want to write an AST. So an AST can be just a type with some meta information and a descriptor. The descriptor is just a list of constructs. So we have term bool, term if, term end. To build such a term, what you could do is just by hand write the element that we can see in the middle. Another thing what you could do is use what we call smart constructors, which are functions that will build them for you. So here we have the term if and term end function below. The use for smart constructors is to separate the actual library to the client code, which uses the library. And that allows us to modify the representation if you want without breaking any code. So say we want to change the representation of term end and say it's just a particular case of an if, then we could do that by just removing the constructor and changing the function. So all good, there's no need to modify the code. However, let's say you want to pattern match on said data type. So if we want to recognize a term of some form, here a double conjunction, we would have to break the actual type using the constructors and return the subterms. This means that the client code mentions the actual implementation. This breaks the abstraction layer, meaning that if you do the actual modification I presented in the last slide, you will have to modify the actual client code. Also, there is a small lack of conciseness, because if we compare it to the actual creation of said term, which just uses twice the term end function, here we have to go deeper in the definition. So one may ask, why not just use the exact same syntax to deconstruct our term like we did to construct it? So in that case, we could just match on some term and by some magic inverse the creation of the term, and this would work as wanted. So in this syntax on the left, I reuse the same name as for the constructors, so term end here, but this would be considered some kind of pattern version of term end. So say we created a library of patterns, library of deconstructors, this would be part of it. So part of the say library, we could define all of the deconstructor versions of our functions. So one for term if, one for term bool, and one for term end, if you assume that we encoded it with the definition from before. So these functions will just return return an option with either none if it does not fit the form, or some with the subterm if it does. So let's put that aside for the moment and go to the second feature focus, which is tests that export bindings. So let's look at a very regular usage of hash tables, which in which we just deconstruct some terms, check if it has some key, and check whether this key has some value bound to it in a hash table. If it does, you access it and compute with it. The small issue we have with this code is that we have two accesses to a hash table, meaning that it's not perfectly efficient. A little more efficient version, which is a little more painful to write, would be to use the get_opt function. However, in OCaml, you are not allowed to bind stuff out of a when clause, meaning that you would have to first look at the shape of T, and then inside of the continuation, use the get_up function, meaning that you'd have two places that you could fail, meaning two possible continuations for failure, meaning that you will have to factorize it beforehand. So here again, why not just put the bindings in the when clause? We could just have some kind of Boolean operator which will test an expression against some pattern. This operator is one construct of a kind that we will call binding Boolean expressions from now on, which the syntax will be detailed in the later slide. And this is just a construct that computes some expression and checks it against a pattern, and if this is correct, binds the values. So this could also appear in conditionals. This is a identical code with just an if, and inside the condition we have possible bindings to the then branch. All of that is not new. You also have this in the if-let chains I mentioned earlier in Rust. This is a code taken from one of the Rust RFCs, in which you have a chain of lets that matches some expression on the right and some patterns on the left of the equal, and you have a chain of them. Finally, this conditional also could be used in a while construct. Say you want to check inside of a queue and do a loop on it until the queue is empty. Then you can check whether the queue is empty and then access it, but that's to access to your queue. You might want to just try, attempt to get the element from the queue, and if it doesn't work, you know when you stop. Here is a little more complex example, which uses the same principle for the merge operation of a merge sort. You just access the top of two stacks in the same condition, and if it works, you do your operation. Okay? So I promised some syntax, so let's go to it. Afterwards, we'll look at typing and semantic rules, and a compilation scheme to an ML-like, naive ML-like language to show that this is not magic. So we start with grammar of terms, which is just lambda calculus, regular lambda calculus, to which we added a switch construct. The switch is written with a list of branches. All of those branches are cases with a binding Boolean expression as a condition, of which the syntax will be detailed later. And if the binding Boolean expression is considered correct, we get the result bindings and give them to the continuation. So we can encode the regular constructs of pattern matching, such as the match, for which we just use the is construct that will be detailed next slide, sorry, and that we've mentioned before, which tests some expression against a pattern. Since the T on the match is evaluated only once, we have to evaluate it first, but this is not that much of added code, so it's okay. For the if then else construct, this is similar. We test the condition in some case. If the case is true, we go to the then branch. If not, we go to a trivial true branch, and we're done. So for BBEs, we first have the is construct, which I've talked about earlier. which tests some expression against a pattern. There are also conjunction and disjunctions. The conjunction is a binding conjunction, meaning that you can test the first binding Boolean expression. If it is deemed correct, you get all of the result bindings to be used in the second one. This is exactly what we've talked about with the hash table thing. You test against some pattern, and if it is correct, you can follow through to the other one. Disjunction is as expected. You test against two BBEs, and if one of them is correct, you bind through, giving intersection. You can also have a negation of binding Boolean expression. This is also quite easy to understand. So in the TESP, we have a pattern, which has a syntax. So the three first constructs are fairly regular, with pattern variable, disjunction, and intersection. The when construct just asks for another condition on top of it, which is very similar to the OCaml when, but is allowed to be deeper than the top level. Also, we have what we call an inverser pattern and what is called view or active pattern, or we also call it deconstructors. It takes a function f, which is any function of the type t to some n-ary option, and will evaluate the given expression in some test. You evaluate the given expression f of x here. If you look at the encoding with 1, you test f of x, and if f of x succeeds, you forward all of the result bindings into the asked patterns. So this allows you to have deep tests, such as the double term end that we saw a few slides ago. We also have some predicates that can just be seen as a particular version of an inverser pattern, because a Boolean is equivalent to having an option of units. Just to be said, there is no loss at not having data constructors, since they are just trivial smart deconstructors. Okay, hypermodal typing and semantics. We have 3 typing judgments: one for term, which just gives a type to the term; one for binding Boolean expressions, which gives as type a map of all of the promised variables to the types. Sorry, so maps of the types to the bounded variables. For patterns, all the patterns are expected to be matched against something. We take T as the type of that something, the term that is matched against P, and B is here again the possible premise result bindings. We do not check for exhaustiveness, so this will be a problem for later. I mean, this will be something that we have to mention later. So the typing itself is fairly regular. Typing of a switch revolves on the typing of every branch. We need every branch to be of the same type. The type of a branch asks for the binding of the condition and takes the bindings of the condition and gives it to the term itself. The typing of an is construct for BBE asks for the type of the term, and if the term is of the correct type, feeds it to the pattern, and we return the result type. For the end here, the bindings of the first BBE is fed through to the second one, and we give the union as a result. Note that there is a disjointness operator. We ask for both of them to be disjoint, since we disallow shadowing as an arbitrary choice. Finally, as a very small side note, we ask for both binding Boolean expressions on both sides of an OR construct to be of the same type of bindings. This is not a problem, as we will see in the next slide. we add a restrict construct that allows for scoping variables without, like, for free, to allow for some variables to be used as local computation inside of BBEs. This means that we could, again for free, before the typing process, compute the possible intersection of the binding of each BBE and just restrict both sides to remove any issue. To type patterns, all of that is fairly regular once again. The important rule is for the inverser pattern. Here again, we ask for the type to be some type to some n-ary option. And we ask for every pattern to take the corresponding type as input and give a corresponding binding as output. If all of those corresponding bindings are disjoint, then we return the union. Okay. So we have typings. Now let's go to semantics, and then we will be done with rules. We have 3 judgments. Evaluation judgments for terms is regular again. We evaluate to some value. Evaluation result for BBEs and for patterns gives us some results R being either a mismatch if the match fails, or a match to some map, which maps variables to their corresponding bindings if the binding is correct. So all of the semantic rules will not mention mutable store, but we assume during our research that we could allow for some side effects. So we will have to look at, to be aware of order of execution, sorry. The execution of a switch construct just looks at the first condition. If the condition is deemed false, then we execute the rest and evaluate some value. If it is deemed correct, then we get the result bindings, substitute them to the continuation, and get the result. The test of a BBE takes the result binding of the expression and feeds it to the pattern. The evaluation of BBEs is quite standard again. The end construct is as advertised. If the first one is considered false, everything is false. If the first one is correct, then we look at the result of the substitution of the second one, meaning that we flow through all of the bindings. And if it is correct, then we return the union, assuming that both are disjoint. But if it is well typed, they probably are. For the OR construct and the restricts, this is quite okay in the sense that we test the first one, and if it works, we return it, and if it doesn't, we return the result of the second one. And for restrict, we just have an operation that will restrict the possible result bindings, if any. For patterns, here again, this is also regular. The when construct is the evaluation of the when construct is similar to the evaluation of the AND BBE. We feed through the possible bindings of the first check. If the first check succeeds, then we feed it to the second one. And if the second one succeeds as well, then we return the union. For inverser patterns, we evaluate f of v, and if the f of v evaluates to some tuple of values, then we check every value one-on-one and get the result bindings, and if it works, return the union. Finally, for the predicates, we just look at the results of the evaluation and either give a mismatch or match of empty, depending on if it is correct or not. We have a theoretical result for that, which is type preservation, meaning that if one term is well typed and does evaluate correctly to some value, then the value is of the advertised type. Similarly, for binding Boolean expressions, if a BBE evaluates to some bindings and there were some promised bindings, then those bindings, every variable bound, the value in every variable bound has the promised type from the typing. Here again, for patterns, this is fairly symmetrical. So, as a future work, we would like to give process. So, as I was saying earlier, we don't have any exhaustivity checking because of the when construct, there is an arbitrary deep evaluation of terms inside. So there is almost no way to know for sure perfectly whether we will reach or not the end of a switch construct. However, we could, and this is a work in progress, we could prove progress assuming that we do not exhaust any branch, or in other words, proving that the only way to fail is to exhaust branches. Finally, I said that we have theoretical results. Unfortunately, this result is only done on paper for the moment, but we are hoping to do that as a formalization on ROC as soon as possible. So, I will end this talk with presentation of a naive compilation scheme to some easy ML-like language. So we have some translation operation. Here the double bracket is the term in our new ML language. So double bracket of T is just translation of a term. Double bracket of some BBE with U and U prime represents the translation of some BBE with a success or a failure continuation depending on its results. And similarly for patterns, when given some value, the evaluation result would be some continuation for failure or for success. Quickly, this translation is fairly mechanical and does not have very interesting technical details. We can just stress them a little bit. For the switch construct, we first evaluate the BBE as detailed by the order of evaluation. If it succeeds, go to the translation of the continuation, and if not, we go to the translation of the rest of the switch. Testing an is just evaluating the term first and then feeding it to the translation of the pattern. And finally, evaluating a smart constructor is just getting the output of the translation of the function with the value and checking whether it fits some pattern. If it does, we check one by one every variable with its corresponding pattern. Finally, for the when, we do pretty much the same. Test P. If it succeeds, we test B. If it doesn't, we directly go to the failure. So, we also have a theoretical result for that, which is the correctness of our translation. So, we detail in the paper the syntax of the language as well as semantics, and we want to prove that if our source correctly evaluates with some conditions needed to have a strong enough induction hypothesis, then necessarily its translation will correctly evaluate. So, as a conclusion, first of all, for the future work, we would hope to have some formalization as soon as possible. As implementation, we have started to integrate all of that in the Optitus framework, which is an interactive source-to-source compilation scheme for functional languages and imperative C. All of that is only starting, so we would like to work on it. Also, maybe some pre-processing for OCaml. Although since we designed a compilation scheme to ML, maybe we could pre-process and pass our syntax and feed it to ML, to an ML language like OCaml. And maybe, if possible, to have some conservative language extension. So, one feature that we do not for the moment hold is backtracking. Backtracking patterns. If we fail in some continuation, there is no way to come back to the next case. So we will have to commit to some case if it succeeds. So maybe we could add that with inspiration of exit blocks. And if any of you have any suggestion of programming patterns that we have not or might have not covered, I am very welcome to hear them. Thank you very much for listening to me.
Yeah, thank you for the talk. I think we have time for one quick question while the next speaker is setting up.
Oh, sorry.
Do you have...
I mean, I could ask several questions, but let me pick this one. So one thing that is interesting here. So as a programmer, I would like to have some of this feature. As a language designer, what bothers me a little bit is that you now have all this duplication, like your pattern language and your BBE sub-language. They seem to be very similar in structure, and I wonder if you have some ideas for like avoiding that duplication and maybe being able to express one in terms of the other.
So in fact, in the implementation, so in the very small implementation we have, all of them are the same type.
Mm-hmm.
And just with, I'll just take the mics off. And all of them have the same type, just with like unwritten rule not to use them in another case. We think that we could, for example, use BBEs as some particular terms with a type says that it binds something. And since the patterns are very symmetrical, we also think, as you were asking, that we could take, take a pattern and just put it in the syntax of BBEs, just with some added prefix if needed.
Thanks.
All right, let's thank the speaker again. And our final talk of the session will be compositional deep argument flattening. Please go ahead.
Thank you very much for the introduction. Yes, so this talk is in particular about how to optimize programs that are organized in various programming units and then allow for optimizations across program unit boundaries. And just go into a very simple example. Here we have the compilation of the dot product function, and we would really like an optimizing compiler to pass arguments in unflattened in registers, but as a programmer you would very much like to just write it at a high level. So here's an example where you have a 2D vector as a pair of reals. And then you have a particular zero value. You have the dot product here designed as a curried function. It will also return a real, and then it will do its internals here by making the product of the pairwise elements and then sum those. So at a high level, the dot P has this type v2 to v2 to real. And the problem here is that if we compile that function in one unit and don't know much about the function besides its types, we will just have all values of type v2 being boxed, and also reals will probably also be boxed in some, at least most languages that use this uniform representation of values. And now also closures, at least in some values, will some implementations here will have a default thing of being of being boxed, which will mean that, that there's a lot of boxing going on, and there will be a lot of unboxing going on when you try to apply this function across program units. Now, in particular, there are some difficulties here with when you want to compile it and have polymorphic calls for and that you have this uniform representation of values. So once you introduce polymorphism, you run into these problems that you can have functions that will extract components that are polymorphic, and that means that you don't really know how to deal with them. Also, you might have a garbage collector that requires a uniform representation. So, in particular, separate compilation will require these calling conventions to be based on these types. But there are some strategies to go about these issues. So, first of all, you could, of course, have a compiler that uses a whole program compilation approach. Like Milton, for instance. There you can then apply monomorphization, defunctionalization, and of course you get this problem, this tension between having to recompile everything upon a change of source code, and then the other thing will be to well, you will have this problem that either that or you will have to have this uniform representation. You could also use some kind of runtime type information to allow functions to be you could allow type specialized code and have various mechanisms for copying code and having different versions of the code and so on. What we'll do here is to allow for refined static type information to be pressed across program unit boundaries at compile time. So we'll use this smart recompilation scheme where you will separately compile units, but you are allowed to use information produced when compiling one unit. You can use that information when you're compiling components that use that first component. So you will actually build according to a DAG. And then we'll assume that there are no cyclic linking going on and cyclic dependencies between program units. So ideally here we would like these arguments to functions to be passed in registers, and in this case for the .p function that should be in floating point registers. So we will kind of make it so that we'll take a few passes and try to do it step by step. So first we will kind of think of it as being an oncurring step happening, so that now we have two arguments instead of one, and we will look at only the function definition to make the decision about whether to perform some of these transformations. So in this case here, we will see that there's immediately a lambda after the first argument is given. It is really a curried function, so we can do the oncurring. And then we can, after that, we can unbox the tuples, and we'll see in a moment how to go about that. But each of the tuples here will be unboxed so that we now have a number of reals. They are still boxed in the uniform representation. So we'll have another go at it, and then make the final decision that we'll actually unbox each of the reals, and then for this particular talk here and this work here, for simplicity, we're not dealing with result values. So here we're only talking about the arguments. We believe we could do some dual with respect to the return values. So we'll go about it by introducing a notion of argument transformers that can then be composed. And the reason for this is that we would like the optimizer internals to be able to have different rounds and maybe open up for intermediate possibilities for other kinds of optimizations that will then again trigger flattening decisions. And then at the end of the day, we'll end up having one argument transformer that we can use whenever we visit one of these other program units. And then in one go, we can transform that call site without again looking at the define function. So we have these compositional argument transformers, as we call them, mu here, and we'll have these various operations on in the small language here. We can drop an element from a list of arguments. We can add a new element as the taking from the jth tuple projection of the ith argument as an additional argument. So if we see that there's a pair as one of the argument, we can actually project out of that pair and then add an additional argument to the function, which is then unboxed one level. Similar, we can do if we see something is a real, some parameter is a real argument, we can add an unboxed version of that argument to the argument list. Then we have this uncurry operation that if we see that there's that this is actually a curried function, then we can have the uncurry transform, and then we can compose these using function using composition here. We also have the identity transformer that won't do any change. Now, so here's what happens when you do the dot product. So we'll read these transformers from the right here. So we will start by doing an uncurry transformation. And the idea is that will we'll start with this type here, v2 to real, and that will then be giving us this type back after doing the uncurrying. And now we start adding projections from these elements. We would start by seeing that we'll pick the first element here, and then we will project the first element out of that tuple and add that as a new argument to the function. That will leave us something v2 real. Okay, so now we have three arguments, and then we'll go about adding the other reals for the other components. And now we have these two pairs, and we also have 4 reals. So now we can look at the and decide that, well, now we actually don't need the tuples anymore for the functions. So we can go and drop those and drop those off. And then we can project from the reals, getting 4 floats, and then we can drop the 4 reals. And that will end up, that now we have 4 floats coming in registers. So now, of course, there's some possibility of having a kind of an algebra here. Some things commute and some do not commute. You can, of course, drop 2 things in a row, but you have more difficulties when you start to project, because then they get added to the end and so on. So you have to kind of, and this is about these argument transformers. This is also why it's quite nice in a compilation framework to have some kind of one module for dealing with these transformation of arguments, because you can very quickly get things wrong if you're not careful, it turns out. So having this thing, as you say, as a side note, also simplifies many things in the compiler infrastructure and all the optimizations that was done previously, which were more ad hoc than what we see here. So we can define formally what it means to define to apply these argument transformers to types, and this is really just as you would expect. If you drop the ith element of a function type here of the argument, then you basically just filtering out that the ith element of the argument. When you project, you're really projecting from the with number j here from ti, from element ti in that vector here, and that you're adding that one as an additional argument to the function. And for floats, you get the obvious thing here, that you're adding a new float where you have to assume that this thing is already a real. Uncurrying also works as quite simply. If you see this type, you can uncurrying and get this one, and then composition will work naturally. So now the question is, how do we actually infer these argument transformers? If we are looking at, the idea is to only look at the function body and not the call sites. So remember, we want to be able to do it in a compositional way also when we compile modules. So we will only look at the particular function definitions, and then we will make decisions based on the fact that, or the property that we would like not to go and do duplicate work, and we would like not to allocate, cause additional allocations based on making these transformations. So the decisions have to be safe in the way that we are not doing or having the resulting program do more work. And in particular, they should not allocate if the previous one did not allocate. For drop here, we look at the function body, and then we see we can introduce a drop if we see that the arguments are not used within the body of the function. For the projections here, we identify those arguments for which only projections are used. So if a function is actually using a tuple as a first-class value, maybe storing it into a reference, maybe passing it to another function that expect such a pair, for instance, or tuple, then we are not allowed to make these decisions. Similar for reals, if we really are using this real, storing it somewhere in a box setting, then we are not allowed to make the transformation. For uncurrying, it's quite obvious. You just look at, is there actually a lambda? Then you do the uncurrying. And then at the call side, once you see these things, you will actually modify it, and also use the argument transformer to transform the call side. The idea here is then that you can also, in one go, when you're analyzing, you can actually repeatedly look at the function body for a function and simplify it and make decisions on that function itself and come up with a composition of transformations you can do. And then in one go, you can have made some decisions. It might be later on that more transformation will happen based on maybe inlining decisions, local beta reductions, or other transformations that you do within the ordinary optimization framework. So again, this mechanism uses a smart this is based on the smart recompilation scheme, where you can then avoid looking at avoid recompilation if nothing has changed since the last time you compiled the unit. Now, what we would like to end up with is to have the function. So here you see what it will look like in an internal representation. The dot products, you pass registers, and now you are really doing the computation on floats, and then you are boxing it to a real value, because this is what the function type says, and then you're exporting this function so that it's available for other program units. And now at each call site, you will then apply this argument transformer to transform the call. So this is the only slide with some inference rules here, but that will just show you how to actually transform the call sites based on these decisions. So whenever you have an argument transformer mu here and a call site of some type where you apply f to a number of arguments, then that will be transformed into a new call to f with a modified set of arguments. And then they will have a change in type, and you will also return here some bindings that will lead to at the call site you can basically do an eta expansion of this small environment being created, and then you will actually create the lambda at that point. So in particular, we see here that the uncurrying will lead to an environment x : tau here, which will say that at a call site you'll need to wrap a lambda around that to create the current function, because you're only partially applying it. And then you see what will happen with a drop there. You just drop the parameter and so on. So all call sites can be computed this way. So there's a paper also linked to. We can then show that you have under the proper conditions here, where this phi here maps these function identifiers to these compositional argument transformers. Then you have the property that if these two arguments are related in the source and the target environment, then you can go and transform any expression containing function calls into another one, and then you will get that you will be preserving types here. So quite standard and quite simple in the setup. So here's now then the how it looks and how it's used inside the MLKit REML optimizer. The point here is, and one point I want to make, is that of course this is a real compiler framework where you're doing a lot of inlining across modules. You're allowing for function specialization, in particular specialization of recursive functions, to be happening across modules. For instance, fold, map, things like that. It's very useful to actually inline those functions to get efficient code. And such a setting might interfere somewhat with this flattening. So now, how we are organizing this is that we will actually do two passes of the two loops here. We will have the optimizer take in a compilation environment, E, and then we'll take this flattening environment, P, and then an expression. And at the end of the day, it will return an export environment, E prime, capital E prime, and an external and an export flattening environment, P prime. And now there are some assumptions here when you do this. There's of course some test for whether we should keep on going. If some transformations happen, we keep on going, and that's kind of hidden under some this reset changes function. And then we'll use internally this shrinking lambda expressions in linear time by Appel, Jim, from this GFP paper, where we maintain the number of occurring variables in expressions, so that you basically have two steps in the process. And so first you figure out how many uses of a variable at the bottom up. But when you see the binding and you see that there are 0 uses of the variable, then you can just delete that binding. So you have this in linear time. You go down, you go up, and you do a lot of work in that process. But now again, there are other optimizations like that also can happen, and that's part of put a little bit under the hood here. Dead code elimination I mentioned, inlining and folding, and common sub-expression elimination, which cannot be naturally captured in this contract flatten or contract reduce scheme in shrinking lambda expressions. So there are a little bit more going on. So we'll repeat the process until we reach kind of that there are no more opportunities for optimizations. Now it's worth noticing that since these flattenings are happening across program units, we can only use this P once. So it doesn't work well if we try to modify the parameters of a function and do it multiple times. We should apply this flattening transformer only once to a particular call site, right? Now, then it is a question, on the other hand, the environment E contains everything about the function as it's introduced in the module maybe that's imported. And that means that can be inline, that you can look for multiple cases where maybe you can use static information about that function to try and see whether you can apply that knowledge to make some decisions about inlining or so. So that's allowed to be used multiple times, But it should probably not be used after you apply the flattening, because now the arguments comes in a different order. So there's something here about how to maintain the external coming from other modules, about how not to mix up whether you use E or you use P first, and so on. So you can use E many times, but not after you use capital P. So, so that means that there are some subtleties here in this cross-compilation unit. Here's kind of this generic compilation scheme that we are using. So we have for each, it's kind of a nano compilation scheme where you have a lot of transformations going on in the compiler. Each of these transformations is allowed to take an import environment at any level. That could be information, usually E1 will be the type environment for doing a static elaboration. E2 might be compilation to intermediate IR. E3 might be an optimization environment, the flattening environment, region type environment. It could also be much lower level, calling conventions for the functions and so on. All these things can be passed across module boundaries. Now, so you have a scheme here where you are transforming E1 to En from the source expressions to machine code. And at any level you have these imports, and at any level you have exports. And then the scheme basically serializes all these things to disk and check whether the assumptions has changed. And if they haven't changed, then you don't need to recompile a program unit unless there has been source code changes. So we have done some empirical evaluation for this work. So here we are comparing different instantiations of the ML kit with oncurring enabled, with tuple argument unboxing enabled, and with real argument unboxing enabled. And we're also comparing with Milton just to see where are we, in what ballpark are we playing here. So first of all, I should say that we have, so here are some measurements on a number of benchmarks. So these two compilers are very different in nature. Of course, you have the whole program optimizing compiler for Milton. And we can see for some of the cases that Milton runs code which is twice as fast as the ML kit. Milton does all this also data flattening. So inside data constructors, you actually flatten components. Reals are flattened inside these data structures, and you also have tuples, nested tuples are also flattened and so on. You even have mutable references that are, there's an analysis which figure out whether that can be stored inside, unboxed in the data structure. So those things will trigger and assumes, of course, a whole program compilation scheme, or at least you need to know that things are not escaping those contexts, and you're not having any problems with polymorphism and so on. But we also see some examples that are not that doesn't really require these features. That, for instance, Mandelbrot here, that we can actually do quite well with this thing, and we are kind of reaching what Milton is doing for that particular benchmark because it doesn't have the need for these data structures and so on. But other than that, I mean, we're doing quite well in some cases for various reasons. The implementation doesn't, the ML kit is based on region inference and has a region memory management scheme, and we see the benefit for that, for instance, in the msort merge sort here, where it runs better because it can actually do quite a lot without having a reference tracing garbage collector. So that's what I probably wanted to say about the empirical result. In a few cases, the ML kit remotely outperforms Milton, but in most cases it doesn't, and more work is needed to actually get towards that level of performance. There's a lot of related work in this area. I should mention at least Milton has had this steep flattening for a long time, and there's a paper back from 2008 on how to do these things, but that's kind of in the context of having a whole compilation scheme. And then there's also this work, arity racing in Manticore, about this adding additional arguments. And you can have a kind of a feature where you leave around both the tuple and the unbox thing, and then be kind of more. Sometimes you use the tuple as an argument. Sometimes inside the body of the function. Sometimes you use the unboxed value. So you can be flexible in that way. A lot of work on unboxing analysis, which is related here, and on representation polymorphism and bit stealing and so on to get performance here across these boundaries. And I think with that, what should I conclude here? It works well across compilation unit boundaries. It's quite straightforward to have type soundness, and it helped a lot to simplify the internals and not have too many ad hoc passes in the compiler and optimization framework, and quite good empirical results. More to be done, maybe integrating with lambda lifting and this notion of minimizing the sizes of closures and so on, and avoid closures when possible. Yes, and so with that, thank you.
All right, thank you for this talk. We'll have time for one question.
Them. So could you maybe explain a little bit more about that? Like, what is the benefit there?
I think mostly the benefit there is to separate the concerns. We could definitely have made it so that you drop at the same time, but there has been this wanted to keep open the possibility that you could actually leave around both the boxed version of the thing and and then have a new unboxed thing. So, for instance, in conditionals, one branch could use directly an unboxed value, and the other one would actually use the boxed one, and then you would still have the case that it won't allocate in that case. So I was just keeping it open for that particular case, and it. Yeah.
If I can ask a quick follow-up, does that mean that for projections of more sort of nested boxed values, you would expect you're still always dropping them? You don't want to produce copies there?
Yes, the current implementation now is only making the decisions, is strict on the case that if you use something unboxed, or use something in the boxed way, then it's not going to do the optimizations. And I haven't played around with this trick of in practice, that having both around.
Okay, thank you.
Right, let's thank the speaker again. So that's the end of the ML workshop.
Talks. One thing that I think a challenge kind of moving forward for the ML workshop is just the number of submissions that we get every year. We had enough this year. We got a nice full program, but just barely, right? So I would love to try to grow the community, try to advertise, try to spread the word. So if you know anybody that maybe doesn't know about the ML workshop, but you think might like to participate, I highly encourage, maybe tell them about it. Share the program, show them the YouTube talks. I think all the talks will be available on YouTube. You can give people a sense of what goes on here at the ML workshop. Anyway, I think we had great attendance today. I think the ML workshop did really well this year. So thank you all for coming, and well, let's go take a break.